Give it a second. All right, cool. So before we even tackle this type of a question, let me tell you about the easiest type of set questions. The easiest type of set questions are the questions that just are first degree sets, which means that the exponent is to the power of 1. So something like x minus 1 is greater than or equal to 4. We know that we are trying to isolate x. The objective is always to find x. So x is going to be greater than or equal to 5. This is the easiest type of set question. Then we go up another level. The next level is when we put it in between something else. So we could say x, 2x, let's say negative 2x plus 4. We put it in between 2 and negative 2 and 4. The objective, again, is always to find x. So when we subtract 4 from the middle, for this thing to still remain true, we'd have to subtract 4 everywhere. So that'll be 2 minus 4 is less than equal to negative 2x less than equal to 4 minus 4. So essentially we have negative 2 is less than or equal to negative 2x is less than or equal to 0. We divide both sides by negative 2. We find then that 1 is greater than or equal to x is greater than or equal to 0. And then just to rewrite it nicely, we can say that x is then greater than or equal to 0 and less than or equal to 1. All right, this is fairly easy. Whenever you're dividing by negative, make sure that you change the direction of the inequality, right? It's almost like you're saying negative 4 is smaller than negative 2. And then let's say I were to divide it by a negative number, negative 1. Then that makes this 4. And if I were to still say less than 2, then this is no longer true. As soon as I start to divide or multiply by a negative number, I have to change the side of the inequality because the inequality will no longer hold true once I multiply by that negative number. That's an important thing to bear in mind. Now, the next level inequality that you're going to get is the inequalities to orders greater than 1. So what is an order? An order is just basically the exponent. So in this particular case, by the way, I don't know if anybody's writing messages in the chat. If you are, please unmute yourself because I can't see them. Yeah, anyway, so orders would be something like, let's say x squared minus 4. This is the second order. And then let's say I were to say it's greater than or equal to, and then let me just say minus 3 is greater than or equal to 1. Okay, whenever you have a inequality that where the degree is greater than 1, where the exponent here is greater than 1, always factorize. I'm going to factorize going to be x squared minus 4 is greater than or equal to 0. And the most beautiful thing about this is that you must understand that we only worry about the x-axis, right? Because what happens over here, we are trying to say that a certain function is above the x-axis. That's what this expression means. This means function is above x-axis. We don't care about the y-axis is doing. So we know that this is the x-axis of this particular graph. We don't need to worry about what the rest of the graph is doing. We just need to worry about the fact that, of course, the roots are going to be negative 2 and 2, because these are the values that will make this expression equal to 0. It helps us to find when it's equal to 0, and then from there we can work our way backwards to find when it is greater than or less than 0. Right, it's important to find when it's equal to 0 first. That's why we factorize. So then I can factorize it as follows. I have x plus 2 and I have x minus 2 is greater than or equal to 0. Now you're basically saying, when is this parabola, this x squared minus 4 parabola, greater than or equal to 0? The point of factorizing is first in order to find these roots over here. You're basically saying that when you plug in negative 2, you have negative 2 plus 2. This bracket is equal to 0. This entire expression then ends up being equal to 0. You plug in 2, this bracket ends up being equal to 0. Then this entire expression then ends up being equal to 0. Right? So we know when it's equal to 0. It's at negative 2 and 2. Then we can actually answer the question. The question asks us when we are greater than or equal to 0. Yes.
I can't see like what you're referring to.
Okay, you'd have to be more precise than that. What do you mean by you can't see what I'm referring
Are you
to?
actually like writing down something? Because I can't see.
Okay, can people see? Is everybody else able to see what I'm writing down? I can try to like stop the presentation and represent. Okay, I'm seeing a thumbs up. Okay, I'm stopping to present. So I'm gonna share again. I see someone raise their hand. If you're raising your hand, please unmute yourself. Or unless you meant to just react and say like thumbs up, whatever. But if you are raising your hand, please do unmute yourself.
Now I can see.
Now you can see. Okay, perfect. Okay, cool. So the important thing is for us to first of all find when we are equal to 0, and then we can work our way backwards from there, because we know that when we are equal to 0, that's when we hitting the roots over here. Then we can answer the question when are we greater than or equal to 0, and then when is this graph greater than or equal to 0? In other words, when is the graph above the x-axis? Because when the graph is above the x-axis, x squared minus 4, which happens to be the y, right? So x squared minus 4 is basically just the y value. We say y is equal to x squared minus 4, right? So when we are greater than or equal to 0, we understand that that's when the y is going to be, that's when the graph is going to be above the x-axis. So we just observe when the graph is above the x-axis. That would be over here, and that would be over here, right? So the same approach would be done when we're dealing with second order derivatives as well as third order derivatives. That's typically as far as they do get, but even if they get higher, the main objective is always to factorize. Always factorize and ask yourself the question, which values of x will make this expression equal to 0? Okay. Any questions so far? You will have to unmute yourself again. I'm going to keep on saying this because I can't see the chats unless I actively leave the chat, the place. Okay. All right, so that's just the basic introduction. Now we're actually going to start to deal with the questions that we have over here. All right, so to begin with this first question expects us to determine the solution set of the following inequality. We're given a certain inequality as this. Now this is not a first order derivative, neither is this, no, okay, that is not what I meant to say. That's not the first, it's not a first order, what's the word? It's not a first order expression, neither is a second order expression. We can't really, there's no like exponent per se, but the main objective is always going to be the same, right? If we can say that something is equal to 0 or is greater than or equal to 0, that is easier for us to use as a reference. Okay, so what do I mean by that? Let's say I were to say something like, let's say I were to have a particular graph like this, right? Look at this particular graph, and let's say I want, okay, it thinks I'm trying to erase. And let's say I have this particular value over here, and then there's the value over here, and I'm going to say this is maybe, I don't know, I'm going to say, I'm trying to think, let's say this is like 3 or something. Let's say that's the value over there. The value over there is 3. And then I'm asking you for when the graph is above 3, right? That becomes a bit more difficult when you are writing, because when you try to think about when the graph is above 3, you have to be very careful, right? Because the graph is going to be above 3 in this region. Okay, it's not really highlighting the way I wanted to highlight. The graph is going to be above 3 in this region, right? And then it's going to stop over there. And it's going to be above 3 in this region, and it's going to stop over there, right? It becomes very complicated to try to figure out when it's above 3. What makes it easier is to try to figure out when it's above 0. So you try to rewrite your expression so that you're trying to figure out when it's above 0. And then now it's really easy, because when are we going to be above 0? Well, we're going to be above 0 over here, specifically over here, right? When we are between the roots over here, and again over here between the roots over here. So that's pretty straightforward, right? And that's as simple as it gets. So if you have a look at this particular expression, it's hard for us to try to calculate it just as it is given to us. So it's easier for us to try to rewrite it as something with respect to 0. So I'm going to rewrite it as follows. I'm going to rewrite it as 1 over x minus 1 subtracted by 1 over x plus 1 is greater than or equal to 0. So something with respect to 0, right? And then if I can solve for this, then I'm going to be really fine. Again, this still looks a bit wonky, so I'm going to try to combine these two expressions together. We know that you can only add or subtract things with the same LCD, so I'm going to multiply each of them by 1, but a special type of 1, right? I'm going to multiply this by x plus 1 over x plus 1. You'll notice I'm multiplying by 1, so I haven't changed the identity of the original expression itself, right? I'm still multiplying by 1. It doesn't change the thing. It's just another way to represent the same expression such that it makes it easier for me to do further calculations. Then I'm going to still take this 1 over x plus 1, and I'm going to multiply it again, also rather, by 1, but specifically x minus 1 over x minus 1. That way, both of them end up having the same denominator, and then I can add them up together. Okay, what is the one on the left equal to? It'll be x plus 1 over x minus 1, x plus 1. What does 1 on the right equal? Well, that's going to be minus, and that's going to be 1, or it's going to be x minus 1 over x plus 1, x minus 1. You'll notice that they now both have the same denominator. They're both written with respect to 0, and they're all greater than or equal to 0. Right. So, okay, sorry, I said the same thing twice. Anyway, because they have the same denominator, I can actually add the expressions to each other, right? So that's x plus 1 minus all of this. So make sure you use your brackets. So if you just say minus x minus 1, that's not going to be the right thing, right? You're saying minus this, right? So you need to make sure you're saying minus, and then you're saying you have your brackets over here, x minus 1. That's particularly important. So x plus 1 minus x minus 1 over the same denominator. I'm just going to rewrite this denominator as x squared minus 4. It's the difference of squares. You could leave it as is, but okay, in fact, it's actually probably easier for me to just rewrite it, leave it as this. X minus 1, x plus 1 is greater than or equal to 0. Okay, and then now we're going to have, this is x, I'm just going to write it above here so we can see what's happening over here. This is going to be x plus 1 minus x plus 1, right? You'll notice that the x's cancel out with each other, and then we're just left with 1 plus 1. That's going to be equal to 2. In other words, we have 2 over x minus 1 x plus 1 is greater than or equal to 0. Cool. Now, what do we understand from this thing over here? This thing is telling us something important. We are saying that this expression is greater than or equal to 0. All right. Now, just imagine this. This 2 is never going to change, right? And oftentimes, this is going to be the same if they get, you're going to use the same approach if they gave you something like an absolute value of x, of let's say 3x minus 4, whatever, right? This thing will always be positive, right? So let me ask you this question. I want you guys to think really carefully here. If the numerator is always going to be positive, and you're saying positive number divided by denominator, what sign must the denominator be for this expression to be greater than or equal to 0? Because we know the expression has to be greater than or equal to 0. The numerator is definitely going to be positive regardless of whatever happens. So the denominator has to be something. What sign must the denominator be for this to be true? So this is the question I'm asking. I'm expecting an answer. What do we say? Positive would be correct, right? Because you're saying a positive number divided by another positive number. Obviously, the end result is going to be a positive number. So that's particularly important. So we are essentially trying to solve then for when the denominator is greater than or equal to 0. Because if this denominator is greater than or equal to 0, then the entire expression is going to be greater than or equal to 0. So that's what I'm going to do. I'm going to say x minus 1, x plus 1 is greater than or equal to 0. You'll notice that this is a second order derivative. I keep on saying derivative. This is a second order polynomial in the sense that it's x squared minus, that's not correct. It's x squared minus 1, right? Meaning that we're already given the roots. Remember, whenever there's a second order derivative, or basically where the exponent is greater than 1, the exponents that we're raising x by is greater than 1, we're going to factorize, because that's going to help us to find our roots. So we know that the roots over here are going to be -1 and 1. What does a root mean? A root is just the x values that you would plug into the expression that would make this equation equal to 0. If I were to plug in -1 into this expression, this is equal to 0, so that's 0 multiplied by whatever this is. If I were to plug in 1 into this expression, then this bracket is equal to 0, then you have 0 multiplied by whatever this is. That is a root. How does this parabola look like? We don't need to worry about what it's doing in the y-axis. We just need to worry about what's happening in the x-axis. So this is why I'm just drawing the x-axis over here. So the x-axis is as follows. It's going to be just this simple thing over here. If this is our x-axis, what do I understand from this? I understand that we're going to be greater than 0, specifically in this region going this way, and in this region going that way. So my final answer then, and we look at greater than or equal to 0. So we know that the root is obviously going to be equal to 0, and then we're going to be greater than 0 on either side of the roots. So that's essentially what I'm going to do. I know that then I'm going to be greater than 0 when x is less than or equal to -1, or when x is greater than or equal to 1. Okay, so when do we use or versus when do we use and? We are going to use the word or when these different values in the set don't occur at the same time. And we're going to use and when the values in the set occur at the same time. When we start to talk about absolute values, it's going to make a little bit more sense. In fact, I'm going to do a second order derivative so that you can understand essentially what I mean for this. But essentially, when we're doing this particular thing over here, right, we know that it's going to be towards the left and towards the right. The word we can use here is going to be or. Okay, so that's how we would solve that particular problem. We're going to do 2 more of these types of problems, and then that should be it for sets. And then we're going to move on to absolute values. Are there any questions from anyone so far? And please, if I do speak fast, tell me to slow down. I know there's an issue that I still have to work on. But yeah, do just holler at me and tell me, yo, remind me to slow down. I will speed up again after you remind me, but then remind me again. But yeah, okay, cool. Okay, so I'm going to then do another question, seeing as there's no other questions I'm seeing from anyone here, and that's going to be from the 2022 question paper now. So let me paste it right now, and then here we go. Okay, so you'll notice that this is really similar to what we've dealt with previously as well. In fact, okay, I don't do a question that's too similar. Okay, let me actually try to do a slightly different question. Let's see. Okay, I think no. Give me a second. Okay, because I do want to add variety, because I feel like if we're doing too much of the same question, then you're not gonna, it's not gonna be as effective. Okay, let me see. Question 5, is this a different? All right. Okay, this is more an absolute value type question. Okay, never mind. We're just going to do that question and we can do absolute value questions afterwards because we're doing absolute values in a bit. Okay, cool. So we're going to have this type of a question. Determine the solution set of the following inequality. Similar principle. Did I finish answering the previous question? No, we didn't. Okay, so to answer the previous question, to give the final answers to this previous question, you'll notice that basically we're going to be when x is less than or equal to -1. In other words, from x is an element of, we're going to start at -infinity. We're going to go to -1, and we're going to include -1. We never include infinity because you never really reach infinity. It's just an abstract concept. And then or is the one that looks like a u, right? Or is one that looks like a u. So this is or. If you want to understand the difference, I like to think about and as like it looks like this. It's almost like I can actually write the word and like this, right? So this one is and if you know and, then obviously the other one is or. So this is and because you can say and from here, and yeah, the other one is or. So or, and then when and then we're going to be equal to 1 all the way up until positive infinity. So if you go to the question, then the correct answer would have to be the one that allows for that. Okay, I think, okay, I messed up. One important thing that you should actually always do before you even give a final answer is to lay out your restrictions. So whatever your final answer comes out to be, make sure that you double check it with the restrictions. Né? So yes, I said it's equal to -1 and 1, but -1 and 1 doesn't even exist in this particular function. You'll notice that if I plug in 1 and if I plug in -1, I have a denominator that's going to be equal to 0. We know the denominator cannot be equal to 0. We'll speak about these a little bit more when we're dealing with like functions, because when we're talking about like the domain of a function, these are the things that could like affect a domain of a function, right? So it's not going to be a focal point right now, but just make sure that like whenever you see a fraction, whenever you see a square root sign, whenever you see an exponent, whenever you see these types of things, a log, whenever you see these types of things that could affect a domain, that you bear those in mind. We will deal with those when you're dealing with functions. For now, just understand that obviously, yes, technically, although in our solution we were equal to -1 and we're equal to 1, it doesn't make sense to have that over here because we can't actually have a denominator being equal to 0. So even in my inequality, I should have actually fixed that and taken that into consideration. So that was just an error on my part. You can't have denominator being equal to 0. So not here, but rather in this previous portion, the upper portion is fine. Where I should have not put the equal sign is right over here, because there's no way the denominator, this entire denominator, could be equal to 0, because that's obviously going to give us an undefined number. So that's just something to bear in mind. So in this particular case, now let me do the right thing and start with that. X cannot be equal to 0, and X, no, sorry, this is or. X cannot be equal to 0, or 2x plus 1 cannot be equal to 0. So x cannot be equal to -1/2. So these are two values that the x can't be equal to. So when you actually do your final expression, your final answer, and you find 0 and -1/2 over there, make sure that you get rid of it. Okay, so again, we have a little bit of a fancy, or a little bit of a wonky type of expression, but we know that we're always going to say something is greater than or equal to 0, whatever, and then we're going to take it from there. So 1 over x is -1/2x plus 1. We understand that this has to be greater than 0. Okay, and then I know that I should combine these two because it just helps me to visualize a bit better. So you guys know how to do, so I'm gonna be a little quick. We're gonna say 2x plus 1, 2x plus 1, and that's gonna be minus, and that's gonna be x over here over 2x plus 1, and then x. So I'm just combining these two over here by giving them the same denominator, right? So now that I have this, I've written it as a single entity, I know this is still going to be greater than 0. From here, what am I going to do? Well, I understand that I can rewrite it as, okay, let me just be sure that I did everything correctly. Cool. Okay, so I can rewrite it as, so I'm just so paranoid, 2x plus 1, 2x plus 1, and then this is x, and then this is going to be x. Okay, so okay, it is cool. I don't want to lead you all astray. X plus 1 is over 2x plus 1, right, multiplied by x is greater than 0. Cool. Now, we have the fact that x plus 1 over 2x plus 1 multiplied by x has to be greater than 0. This is not as straightforward as the previous one, because the previous one was a bit more, it was a bit easier for us to figure out, because the denominator was always positive, so the numerator had to be positive as well. But you'll notice in this specific case, the denominator and the numerator can both be positive, or the denominator and the numerator can both be negative, right? In both of those cases where the denominator and the numerator are positive at the same time, that's the key word, at the same time, and the denominator and the numerator, it can also be negative at the same time, the entire expression is going to be positive. What do I mean by that? Whenever I say the word at the same time, the key word here is going to be and, because we use and when expressions are true at the same time. In essence, when x plus 1 is greater than 0 at the same time that 2x plus 1 multiplied by x is greater than 0, right? If they're both positive, then this is true. Because you have a positive divided by a positive, obviously the final answer is going to be greater than 0. But also consider the alternative. The alternative is as follows. The alternative is when x plus 1 is less than 0 at the same time that 2x plus 1 multiplied by x is less than 0. Right, those are the two alternatives that we have over here. Given these two, I have to solve for what x is, and then I'm going to find the intersection of the two sets. Okay, so this barrier over here is, you can imagine it as my OR barrier, and then this is my and this is my and, right? So I need to combine these two sets to be one answer, because they have to be positive at the same time, or they have to be negative at the same time. All right, so now let us actually solve these inequalities. So when x is greater than -1, or, and then this is already written in terms of, it's already factorized, so we can actually just imagine our thing, right, our roots. So obviously this is a happy parabola, that's why I'm drawing it like this. And then the roots, what values of x will make this expression equal to 0? Again, remember, it's better for us to find things with reference to 0. When we set this equal to 0, then we have 0 multiplied by this, the entire expression is equal to 0. So one of the roots is definitely going to be 0. But also this bracket could be equal to 0. In other words, 2x plus 1 could be equal to 0. In other words, the other root, oh gosh. Okay, give me a second. My pen's acting up. Okay, so the other root would be when x is equal to -1 over 2. So we have one root being where x is equal to -1 over 2, and the other root where x is equal to 0, right? Those are the values that we have over here. And then we are specifically looking for when this is greater than 0. When it's greater than 0. So when is this greater than 0? Well, you can clearly see that the parabola is going to be greater than 0 on this side as well as on this side of the inequality. All right. Given that, we can then therefore understand then that we have to find the intersection between this and this, right? Because if this one is negative whilst this one is positive, in other words, when the numerator is positive and the denominator is negative, then this expression can no longer be greater than 0. So it's important, it's imperative that we find the intersection of the two sets. How do you find the intersection of the two sets? Write both sets on the same number line and then find where the number lines overlap. So I write the number line over here. One of the roots is -1. No, that's not right. Negative, okay. The critical values are -1, -1/2, and 0. So -1, -1/2, and 0. Right? These are my critical values. And then I am going to draw the number lines. So for the first parabola, we know that when x is greater than -1. So this is x is greater than -1. And then for the other parabola, it's when we are here. All right, so let me just go, not parabola, I meant sets. This is the one set, right? And then I'm drawing for the other sets. So that's going to be when we are positive. So that's going to be from here this way, as well as from here this way, right? Based off of this diagram that I just basically drew over here. So I drew both of them on the same number line, and then now the final part is to combine these sets as a single set, right? So where do these overlap? And you need to be careful. I'm making a mistake I shouldn't be making. This should be an open circle. This is an open circle, right? They can't overlap on an open circle. That makes no sense. There's no overlap on this open circle over here, right? There's no overlap here, and then that's it, right? So I can basically write it as follows. I can write it as -1 excluding -1 up until -1/2, right? Excluding -1/2. And then I can then say or, and then I can go from 0 up until infinity, right? Because both of these go up until infinity, right? And you can actually check these with like easy values. So let's check an easy value like 1, right? Because 1 falls in this place. So we can understand it should be positive. So let us have a look real quick. So it's going to be 1 plus 1. That's going to be 2 divided by, that's going to be 1. And that's going to be 2 plus 1. That's going to be 3. So in the numerator, we have a positive. In the denominator, we have a positive as well, right? So as you can see over here, this specific set was for when the numerator and denominator are both greater than 0. Now we're going to check the other side, because if you are less than 0, you have a negative divided by negative, the final answer is still to be expected to be positive. So we're going to check the other side that we had left first, and then we're going to find our answer for that one. So for the other side, we know that these two will have to overlap as well. So x has to be less than -1, or, and then again, it's the same parabola, but now the focal point is different. So -1/2, and then we have 1 over here, right? So as you can see, then we're looking for in the parabola is less than 0, which is going to then be in this region over here, because we're saying when is the graph, when is the y-axis, right? This is a y. Remember, the full thing is y is equal to 2x plus 1 multiplied by x, right? On a Cartesian plane, it would look like something like this, or whatever, with -1/2 and 1. And then we're essentially saying we are looking for when we are less than 0. When is y less than 0? Y is going to be less than 0 when we are below the x-axis. All right, so I just wanted to make sure that we understand what we're doing over there. Okay. To go back to what we have over here, it goes as follows. We are between -1/2 to 1, excluding those, right? So again, we're going to draw them, but now on the number line, I'm going to look for the overlaps again. Critical values are going to still be -1, still going to be -1/2, and it's still going to be 1. Again, we're going to draw each of these. So -1, that's going to go from here to here. The other one is going to go from -1/2, so that's going to be open here up until 1, which is going to be open over here. You'll notice that these actually never overlap. It was important for us to check it, but it's not actually possible, right? So there's no way that we can overlap the numerator and denominator in this specific one. So the answer would be determined solely based off of what we have over here, right? It is important to check, right? In this specific case, it didn't, the other side had no contribution, but it could have been true, right? Oh, sorry, let me just make sure, I think I moved too fast through that one. You'll notice that, remember, this set has to be true at the same time that this set is true. But you'll notice that this is x is less than -1, and this other one is x has to be between -1/2 and 1. But you can't be less than -1 at the same time that you are between -1 and 1. So this version can be completely disregarded because there's nothing that we can actually gain from there. And then so the focal point is just going to be this. All right, that is that. Any questions based off of that? So far, we're going to do one quick 2-minute problem on still on sets, and then we're going to jump right into absolute values. Final question, going once, going twice. Gone. Okay, so we're going to jump right into, we're going to do one more sets problem, and then we're going to jump into absolute values. So the set problem is going to be a random problem that I'm going to think up, because I didn't really have the time to see those in past papers, but it's a type of problem that goes as follows. It says x squared, right? And it's going to be x squared minus, I'm going to say minus 3. It's going to be similar to one we did previously, but is greater than -1 and less than 1. So a type of question like this. So you're solving for x, and that is our objective, right? This is just a simplified version, but the approach is going to be the exact same, and we're going to use our friend, which is going to be and. Okay, for these types of questions, right, what do we typically try to do? We typically try to isolate x. So let me try and isolate x the wrong way. The wrong way would be to add 3 on both sides. That's going to be equal to 2, and it's going to be x squared. It's going to be this, and you're going to have 1 over here, right? And you're going to try to square root. Okay, did I do everything correctly? Wait, -1, 1, 2, 3. That's 2. -3. So this should be 4. My bad. Sorry. Okay, so this is essentially what you'd have over here. The wrong way would be to square root both sides, and you square root, you square root, you square root, and then you get √2, you get x, and you get 2. This is wrong. You're not doing the full answer because it's x squared over here. There are 2 possible solutions for x. X could have been -2, x could have been +2. We don't know what x was in that specific scenario. So what do? We isolate and find each individual. Okay, we work with each side of the inequality at a time, right? Because we know how to work with x. We know how to work with x squared minus 3 is greater than -1. I'm just rewriting this portion. I just want to have x squared minus 3 on the left-hand side. It just makes my life easier, right? This is the left-hand side, right? So x squared minus 3 in this scenario has to be greater than -1. But we know that in the same problem, in the same set of solutions, it also has to be less than +1. So if it also, at the same time that is greater than -1, also has to be less than 1, I have to use our special word, our friend over here, which is our and, right? And x squared,
Sorry.
yeah, that is, yeah, boo.
Please slow down.
So that, all right, we're gonna try. I am gonna probably speed up again, but do remind me. Okay, so it's a slow down. X squared minus 3 has to be greater than -1 in this thing that we're given, right? I've just rewritten this thing. I just want to have the x squared minus 3 on the left-hand side. So x squared minus 3 greater than -1. Portion number 1. But at the same time that it's greater than -1, it also happens to be less than +1. So I'm going to work with these individually, and I'm going to combine them afterwards. So let me work with them, the left-hand side first. I know that whenever we have second-order derivatives, not derivatives, polynomials, all right, I'm going to factorize. So that's what I'm going to do. I'm going to say x squared minus 3 plus 1. So x squared minus 2 is greater than 0. Right? Were I to factorize this expression, which you should always do, you'll find that it's going to be absurd, but it is still going to be factorizable. It's going to be x plus √2, x minus √2, right? It's just a difference of squares, right? So obviously, if you multiply these out, it'll end up being x squared minus 2. I haven't changed anything. So I have x plus √2 and x minus √2. In other words, this is a parabola, obviously a happy parabola that has the roots of -√2 and √2 itself. Those are, in other words, those are the values that you could plug into this expression that would make either of the brackets equal to 0, which would make the entire expression, the entire graph equal to 0. So I'm going to do this. I'm going to say -√2, and I'm going to say +√2. By the way, I'm not going to send the recording on the group chats because I don't want to like spam too much. So when I send the recording, please do join. Okay, I actually don't know how optimal this is, but I'm going to try and send a link real quick to. Okay, so if you join this group chat, I'm gonna announce when the recording is available, and I'm gonna send you guys the recording on that group chat. So I'm gonna probably remind you guys like every 40 minutes or so, because I know if you join late or whatever, you don't get to see the chats that came before. So please do join that one so that like when I do send the recordings, I'll inform you guys. It'll be around midnight, I think, when I send the recording. All right, so cool. Okay, let me just proceed with the thing. So these are the roots, -√2 and +√2, right? And then again, we go back to the original expression. You're asking for when this parabola is above Okay, my apologies. I didn't realize that I was hotspotting from my phone, so it had switched off. So I had to switch back to the Wi-Fi. Okay, so to go back to the okay, but okay, let me just confirm because I have just left the chat. Can you guys see the screen and can you hear me? Just a thumbs up reaction is all I need. All right, cool, thanks. All right, so to go back to what we had over here, we're solving for when the parabola is above the x-axis. In other words, you can see it's in this region and it's in this region. So what is that? Well, that's when x is an element of from negative infinity up until negative root 2, or when we are from root 2 up until infinity. Now you need to be careful. This can't be your final answer, because what does this say? This is basically saying that this x squared minus 3 is less than 1, which is true. X squared minus 3 is less than 1. I'm not sorry, that's not right. X squared minus 3 is greater than 1. But at the same time that x squared minus 3 is greater than negative 1, rather, x squared minus 3 also has to be less than positive 1. So we need to do that side as well to have the full answer. So at the same time, we then have the fact that x squared minus 4 is less than 0. And then obviously this is a pretty straightforward one. You can, well, you should factorize, but this is an easy one that you should know, obviously. So do we know the roots are going to be negative 2 and positive 2? And then we're looking for when we are less than 0 in this specific case. And you can clearly see that we're going to be less than 0 in between this region and this region. So in this region over here. So to finalize that, I would say that's when x is greater than negative 2, but less than positive 2, right? So yeah, okay. And in set notation, I would say x in the element, interval notation rather, x in the elements of negative 2 to positive 2. And then I can write these on the same set of number lines. So it would look something like this. Sorry, it would look something like this. Okay, sorry, let me just, okay. So the first one, in fact, sorry, let me write the critical values first. So it's going to be negative root 2, and then negative, and then root 2, and then we're going to have positive 2, and we're going to have negative 2. So between negative 2 to positive 2 is what this one is, right? And then from negative infinity to negative root 2, so this way, and then this way is for the other one, right? Obviously, these are supposed to be open. Please don't make the mistakes that I'm making. These are supposed to be open. And then we can look for the overlap. So analyzing the overlaps, obviously, I don't think it's probably not going to highlight as I expected to, but they overlap here, right? They overlap in, okay, so let me change the screen real quick. Sorry, review, view, tab layouts, rule, page color, no color. That's what I'm looking for. More colors. White. Okay, this is ridiculously bright, but I just want to be able to highlight. Okay, so we can see that that's going to be in this region over here. That's when they overlap, right? Excluding the negative 2 and negative root 2, and also in this region over here, that's when they overlap again. So to answer the full question, the original question that was given to us, okay, now that's not going to be visible. Let me try and highlight. Okay, it's okay, my bad. Okay, like that was a bad call. I'm gonna go back to having a black screen. All right. So the original expression to asked us for when x squared minus 3 was greater than negative 1 and at the same time less than 1. When are these overlapping, right? And then we find that the overlap then as a final answer will be when x is an element of negative 2, excluding negative 2 to negative root 2, right? That's when they overlap, or when we have root 2 to 2, right? So yeah, that is essentially the final answer. So these are basically the variety of types of questions that you could be asked in the set section that does not include absolute values. You must understand that this is, okay, this is pre-calculus, and then limits, continuity, derivatives is when you get into calculus 1, right? So this pre-calculus and calculus 1 and really calculus 2 and calculus 3 as well, they build on each other, right? So you'll find that you're learning sets, and then you're going to build onto sets. You're going to be using sets information when you're dealing with absolute values. Then you're going to be using absolute value information when you're dealing with functions. Then you're going to be dealing with function principles and dealing with limits. So all of these things add up with each other. So you need to make sure that you have a solid foundation so that you're building on a solid foundation. All right. So cool. That is it for now. So far, before we move on to absolute values. Going once, twice, cool. All right, so it's gonna be absolute values. Give me a second. I have load shedding at 10, but my phone is not charged. So I just need to charge my phone real quick. Give me 30 seconds. Okay, I don't want to waste your time about my charger. So we're gonna. Oh, okay. I just found it. Give me a second. All right. So absolute values. Absolute values, don't complicate it. Okay. Absolute values are your introduction to what we know now understand as piecewise functions. And although we're going to deal with piecewise functions in depth later on, for now, what I need to understand is a piecewise function is a function made up of pieces of other functions, right? So that's the way I like to best explain that. And let me just give a basic example that I do like to give as well when I'm explaining this type of piecewise function. We're going to have a function as follows. Also, okay, by the way, like you need to understand that like the reason why we deal with calculus as it is right now is that once we go into and start to branch into like your different specialties of engineering, right? You may be using piecewise functions when you are programming, right? For those who are going to be focusing on the E&E side of things. You may be dealing with piecewise functions when you're dealing with like physics related stuff. For those of you in civil, mechanical, those types of things. Those are like, that's going to be like your focal points, right? But the basic idea is going to be, is still going to be simple. A function just shows a relationship between X and Y and sometimes Z, right? 3 dimensions if needs be, right? For now, we're going to keep it simple and it's going to be X and we're going to talk about Y. We're going to talk about you. You are traveling, right? You are traveling to go to someone's house or whatever, right? And this travel time takes, well, this travel distance, whatever, takes time, right? And then you are going to be over here, we're going to talk about your speed, right? We're going to talk about your speed. So you are traveling and perhaps you start at rest because you just left your house, right? But you're not going to be traveling at a constant speed the whole entire time. So you're going to start off slow and then you're going to gradually speed up. You're going to gradually speed up. Then you reach the speed limit because now you're at the highway and you're going to be maintaining that speed for quite a while. You maintain that speed, you maintain that speed, you maintain that speed, and then you reach a robot. And at the robot, you're going to start to gradually slow down because you obviously have to stop at the robot. And as soon as you reach the robot, then the lights change and it becomes green. Then you have to continue going again. So so you're going to go like this, right? You'll notice that I have made up 3 different pieces, right? There's the first piece over here. There's another piece over here. And then there's another piece over here. And there's another piece over here. This looks like it's almost like a parabola, a piece of a parabola, right? Looks like an x-squared function. This looks like a function that is y is equal to c, right? This looks like a function with a negative gradient. Y is equal to mx plus c, where m is less than 0. And then this is a function y is equal to mx plus c, where m is greater than 0, right? You'll notice that these are different pieces. These are pieces of different functions, right? This is not a full x-squared function. It's just the right-hand side of an x-squared function, but it's still a function in itself. So these 4 functions in their entirety form a piecewise function, right? So, and they describe different parts of like a process. So that's the idea that I want you to have for piecewise functions, right? And that's because when you deal with like application of now like this section, you'll find that like in real life, things are going to be changing and fluctuating, and we come up with piecewise functions then to say that we're still talking about you traveling. This entire function is still talking about your travel speed, but it also acknowledges the fact that you are human and you're probably not going to travel at the same speed throughout, and your speed is going to be fluctuating depending on a variety of different factors. So that is the principle of a piecewise function itself. We can deal with them now more application-wise in a little while, but that is the basics of a piecewise function, right? So let's start over there. Now we're going to go a little step back and we're going to talk about a specific type of piecewise function, the first type of piecewise function that you learned, and that was the function that says that y is equal to the absolute value of x. At the heart of things, at the very middle of everything, you must understand the following. A piecewise, if something is constrained within the piecewise thing, right, always equal to 0 or positive. It's impossible for something to be inside a piecewise thing and be negative. It could be 0, that is possible, but it can never be negative. So if they ever asked you to solve for x minus 3, when is that going to be less than 0? Or if they're to ask you x minus 3 is equal to negative 5 or whatever, the answer to both of these is x is an element of an empty set or just no solution, right? Or no solution, they mean the same thing, right? There's no possible x values that you could possibly plug into this expression that would give an output that is negative. This is important, and understand the distinction between this and this. They don't mean the same thing, all right? You need to first make sure that you've written everything in terms of x before you can just discard the final answer. So in terms of the absolute value, so in terms of the absolute value, it's going to be positive 2, and you'll find that obviously this can work, right? This can work. Okay, so cool. Now let's take a little step back from that and let's go back to the foundation of an absolute value, and we're going to talk about what is known as the absolute value definition. And the absolute value definition is a piecewise function. The absolute value definition says the following. We are going to imagine a function. We're going to call for ease sake, we're going to call that function x, and we're going to say that this function x, absolute value of x rather, this function absolute value of x does not change under the condition that x is already positive or equal to 0. Because if x is already positive or equal to 0, there's nothing for the absolute value to do. The absolute value takes anything that is positive and leaves it unchanged, or it takes what's negative and makes it positive. Those are the only two things that you could possibly do with an absolute value. So if the thing is already positive, the absolute value can't do a single thing because the absolute value doesn't change anything, leaves absolutely nothing if it's already positive. But if it's negative, then the absolute value takes that and makes it positive. So assuming that x is negative, then we're going to change the sign. We're going to multiply by -1 if x is a negative number. Sorry, my pen is acting out. Give me a second. Okay, it's still acting out. Okay. If x is less than 0. Okay, so what does this say? This says use the function y is equal to x when x is greater than or equal to 0, and use the function negative x if x is less than 0. So these are two functions put in a single function that give you the full shape that you now see and love that looks like this, right? But understand where it comes from. So where does it come from? This comes from the following. Y is equal to, sorry, let me just get the functions themselves. So y is equal to x is a function that goes through the origin with a gradient of 1, right? So rise over run, that's going to be 1. This is going to be 1, right? So this is going y is equal to x function. And then we also have the y is equal to negative x function, which is a function that also goes through the origin, but obviously the gradient is negative. Please imagine this is going through the origin. It's not that clear. In fact, I haven't done it well, but I want you to imagine this going through the origin. All right, so they're meeting at the origin, but obviously this one is the thing is -1 when it's rise of runs -1 and whatever, right? Okay, cool. So that's the basic idea over here. And then we understand the following. We understand that we're going to use the x function, which is this one, y is equal to x, right? We use this when we are above, when the x value is greater than 0. X value is going to be greater than 0 to the right of the y-axis. In essence, we're going to use the y is equal to x function when we are on the right of the x-axis, and then we're going to use the y is equal to negative x function when we are to the left of the x-axis. And then we have the final absolute value function then that looks like this, right? That's essentially where the absolute value comes from, and that's why it looks like this. And then you could take this function itself and you could shift this function, right? And this is a transformation of the function. So if you see x plus 3, right, you'll find that it's going to be something like this, right? So it's going to be something like this. You'll notice that this is never going to be negative. There's no negative y values, rather. There's no negative y values, right? Right, as you can see over here. But I could also say root x minus 3. And then this is, okay, so this is shifted 3 upwards. So you take the original function and you shift everything up by 3. But I could also take the original function and shift everything down by 3. So everything down, shifted down by 3 would look something like this. So that's everything shifted down by 3, so that'll be negative 3. So that's going to be the easiest type of shift. And then the other type of shift is going to then be the shift towards the left and towards the right. Okay, and then that's going to be the ones that do something like, so this is x minus 3 inside over here. And you'll often find in maths when you do it sines and the other types of functions, you'll notice that when you see a negative, oftentimes it's going to be a shift towards the right. So this is actually going to be x minus 3, right? X minus 3 will be shifted towards the right. Every point shifts 3 into the right, and then x plus 3 is going to be as follows. So every point shifts 3 units towards the left, right? And then you can obviously combine these things and stuff, and that's obviously something, it's beyond the scope of this particular session, but that is the basic principle of an absolute value. Okay, now let's talk about the absolute value graph now in terms of its definition. Let's say I were to give you the easiest type of absolute values are going to be the ones with like the ones with let me think about this. The ones, okay, we can do one straight line absolute value. We're going to do one quadratic absolute value, and then we're going to go to absolute value equations. Now then we're going to go to past papers, right? So I just want to make sure you have a holistic understanding of absolute value, and we move on to the past papers. All right. Okay, so essentially we have the following. I could ask you the following. I could ask you y is equal to the absolute value of 2x. Okay, gosh, 2x plus 3, right? Let me just open up GeoGebra real quick so that we can explore this from a mathematical point of view. Okay, so I'm gonna switch the screen. Give me a second. I'm gonna unproject just now. Okay, sorry. Give me a second. I'm gonna start presenting, and I'm gonna start presenting the window the following. Okay, so you should be able to see a GeoGebra screen. So what we're looking at is we're looking at a graphing calculator type thing. If you can't see that, please unmute yourself and let me know, but you should all be able to see that. So I said that we're looking at y is equal to, okay, in fact, let me just think the entire thing, because I want to be able to switch between different pages. Okay, give me a second, entire screen. All right. Cool. Okay, so let me just switch back to, we are looking at 2x plus 3, right? Absolute value of 2x plus 3. But for now, let's first work with 2x plus 3. So y is equal to 2x plus 3, right? You'll find the following. You can see that the graph is going to be positive up until a certain point, right? Okay. Oh, I didn't know I could draw on this thing. Oh gosh. Okay. Now, okay, I've messed up. Give me a second. Y is equal to 2x plus 3, right? So you'll notice that the graph is going to be positive up until a particular point, right? Specifically up until here, right? So this side, we are going to be positive, but below this side, we are going to be negative. So what is the absolute value going to do to this specific expression? The absolute value is going to say that, okay, I'm seeing, I heard the noise. I don't know what the noise means. Let me just switch back to the screen real quick. Okay, I don't know if it's maybe to let me know someone's leaving. Okay, I don't have to answer this question right now, but you have a question for when you reach the specific type of absolute value. What are some applications to the triangle inequality and finding solutions to math problems? Like, how can we identify a problem that needs us to use a triangle inequality, and then how do we use it? I do have a triangle inequality problem from the 2023 past paper. So hopefully when we do that one, it helps. So I have assigned that one out. So yeah, let's just hope that ends up help answering your question. If it doesn't, obviously do ask me again. Yeah. Anyway, let me just okay, gosh. Okay, so cool. And then we're going to look at from this region over here towards this side over here. Every point that is negative is going to be switched to its positive version. So every single point is going to be individually made positive, right? But obviously you can't individually do that like with your hand. So it makes sense to you with an expression. So if I were to put the absolute value over here, you'll notice I'm going to put the absolute value sign, and you'll notice that everything up until wherever this thing is over here is going to remain as is to the right. Right, but then everything from the left is going to change axes. So, I'm sorry, quadrants essentially, right? So, let me just put the things over here. Okay, put one, and then I'm gonna put the other one here. Okay, wait, give me a second. So that's going to be 2x plus 3, and then notice the difference over here, right? Let me just go back again, right? Okay, so again. Right, so I should make sure you're just watching the motion over here. Right, cool. So you'll notice that these are pieces of two separate functions. So let us explore those pieces from now. Okay, so now I'm gonna I prefer to project per window, so I'm gonna stop sharing now because I like sharing the entire screen at a time. So we're gonna go back to the window that we had previously, which was this window. Okay, but this is not what we're doing. Let me okay, cool. We're over here. Right, so how do we apply the absolute value definition? We say that y is equal to, you should replace every instance of x with your expression itself. So I'm just gonna make this a little bit bigger. All right, so y is equal to 2x. Okay, in fact, let me rewrite the original thing first so we have a definition for reference. Is absolute value of x is equal to x if x is already positive, or negative x if x was negative, if the expression was negative, all right, it's less than 0. All right, cool. So let us have a look then at how that looks like over here then. In this particular case, I'm going to say y is equal to the absolute value of 2x plus 3, right? But if the expression itself, that 2x plus 3, right, if the graph itself was already positive, then nothing has to change. It's going to stay 2x plus 3. So 2x plus 3 is going to stay 2x plus 3 if 2x plus 3 was already greater than or equal to 0, right? And then it could also become negative 2x plus 3 if 2x plus 3 is less than 0. Watch out what's happening over here. The x's are being replaced with 2x plus 3, 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 right? And then I'm going to then write this in terms of x, right? Write in terms of x, and then write this in terms of x. I'm going to simplify this. That's going to be the second step. So the second step is to write in terms of x. So that's going to be 2x plus 3, that stays the same. I'm going to simplify this to negative 2x minus 3. This becomes if x is greater than or equal to, and then that's going to be negative 3 over 2. Negative 3. Okay, maybe I shouldn't have done that because now I can't easily switch to the graph so you can see how that looks like as for reference. So entire screen, the screen, that. All right, cool. So you should be able to see my screen. 2x plus 3 if x is greater than or equal to negative 3 over 2, and negative 2x minus 3 if negative, no, sorry, not negative. It's still x, right? As you can see over here, it is still x. The only thing that changes is the negative x. So if they function again, but obviously in this case we know it's x being less than, so I'm saying if x is less than negative 3 over 2, right? So that's essentially the idea over here. And if you go back to the graph over here that we had drawn on GeoGebra, you'll notice that this thing does look like negative 3 over 2. Negative 3 over 2 is the same as negative 1.5, obviously. So if you look at what's happening over here, sorry, let me just erase this. Why can't I erase it? Okay, so give me a second. Okay, so give me a second, sorry. 2x, I think it's plus 3, right? 2x plus 3. All right, so as you can see over here, if I were to zoom in over here, it looks like it's going to be negative 1.5, right? So when we are to the right of negative 1.5, we understand that we're going to leave the function as is. But when we are at the left of negative 1.5, then we're going to use another function, specifically negative 2x minus 3, right? And then if you were to actually write them out individually, so let me write them as individual functions then. So let me first switch this one function off, and I'm going to say the other function is going to be 2. Okay, so we have 2x plus 3 being our one function, and then we have another function being 2. No, sorry, it wasn't 2x. It was, I think it's negative 2x minus 3, I think, right? Negative 2x minus 3, right? So it's going to, the other function is going to be negative 2x minus 3, right? So those are our two functions. As you can see over here, I can switch them both on. I can change them to slightly more. Can I do that? Can I change them to better colors? Okay. I feel like that makes things a little bit more easier for us to see, right? So there, as you can see, this is my red, right? These are the two pieces, but obviously so these are the two entire functions, but this is a piecewise function. I'm not going to deal with both of these as entire functions because, and you should know this, it's going to fail the vertical test or whatever, as you can clearly see, right? It obviously fails the vertical test because you have two y values for a single x value. We know that's not allowed, so that's not going to be a function, all right? But we know that we are using them under certain conditions. So if you see me switch on this value over here, so look, I'm trying to switch on the absolute value function. I hope you can see it when I switch it on, right? So I'm switching it off, and I'm going to switch it back on. In fact, let me just have a more distinct color so as you can see. So I'm going to put it as green. So I'm going to put it as green. I'm going to switch it back on. As you can see, it only takes the positive versions of both of these pieces, right? Well, sorry, it takes the positive versions of the function. Let me rephrase that. It takes the positive pieces of the two functions to form the entire piecewise function, right? That's what I'm trying to say. All right, so that is in essence what a piecewise function does. Any questions on that? The definition of a piecewise function, application of piecewise function, what? Are there any questions there? All right, cool. Everything seems fine. So now I want to deal with one more type of piecewise function, which might throw you off, but I don't want it to throw you off, so I'm going to cover it. So these are piecewise functions for a second degree function. So something like y is equal to, I'm going to keep it simple, the absolute value of x squared minus 4. Something like this, right? So a piecewise function like this, again, the basic principle remains the same. The hardest part is going to be this portion over here, right? But we've already spoken about how we do that. So let's go back over here and let's try to understand what happens here. So I'm going to go here. I'm going to shift it. Oh gosh, that's not right here. Okay, give me a second. I'm going to take this and I'm going to shift it down. All right, cool. So basic principle remains the same. We replace every instance of x in the absolute value. Oh gosh, I need water. Give me a second. Okay, excuse me. Okay, so we're going to use the definition, but we're going to replace every instance of x with the definition, right? So with yeah, okay, let me just explain. Every instance of x with x squared minus 4. So in this specific case, I'm going to put it x squared minus 4 over here. In other words, the function does not change at all if the function was already positive, right? But the function, if the function is negative, then we know to change every y value and make it positive. So if the function was already was negative, right? So that's essentially what we have over here. And then we can expand that. Then I've told you that okay. I've told you that the first thing we're going to try and do is we're going to simplify this thing over here, as well as write this in terms of x. How do you write this in terms of x? Well, we already spoke about that a little bit earlier on. This is the roots of this is -2 and +2, right? So if if you're trying to solve when x squared minus 4 is greater than or equal to 0, we find that the function is greater than or equal to 0 when x is less than -2 and when x is greater than +2. In other words, greater than and equal to, obviously. So x squared minus 4 is if x is less than -2 or x is greater than +2, right? It's going to stay the same. But if the function is negative, then we're going to change the sign. We're going to switch it up. We're going to say -x squared plus 4 if the function is between -2 and 2, because as you can see, when we are between -2 and 2, that's when the graph would have been, as you can see, that's when the graph would have been negative, positive, negative, yeah, right? So we know that we're going to switch the sign then and we're going to have this, right? So if we go back to GeoGebra, is this presenting the entire screen or I forgot to check? We are presenting the entire screen indeed. All right, so to go back to this, all right, to go back to this, we are okay, sorry, let me go to GeoGebra. So, all right, sorry, give me a second. Okay, so in fact, let me close this one. Open something else. All right, so we know that it's going to be x squared minus 4, right? But you'll notice that the region over here, this middle region over here, and you can see it's clearly between -2 and +2. That middle region there is a bit problematic. So we know that at that specific region, we're going to be using g of x, which is obviously going to be equal to then -x squared plus 4, right? But we don't use it for the entirety of the thing, right? We use them under certain conditions. When do we use x squared minus 4? We use x squared minus 4 when x is less than or equal to -2, or when x is greater than or equal to 2, right? I actually don't know if it does that. It doesn't do that, does it? Okay, that's unfortunate. What if I wrote it in set notation? Okay, I have no idea. Okay, never mind. X squared plus 4, we're going to use this one. This one should work. When x is between -2 and +2. That should work. Okay, so that one works. I don't know the correct notation to exclude this thing over here, but basically, obviously, for the green graph, we're only taking the portions where x is less than -2 or where x is greater than 2. So inside the absolute value expression, if I were to have an h of x function that's just equal to the absolute value of x squared minus 4, it takes the positive versions of each of the functions. So x, give me a second, I'm trying to say x squared. I'm trying to say x squared minus 4. As you can see over here, if I were to switch this off, right, it looks like this. All right, so that is that. And that is that on graphing absolute value functions and such. Any questions before we start dealing with past paper questions now with pertaining to absolute values? Cool. Okay, so that was a pretty holistic covering of how absolute values. So I'm going to now start to tackle the questions from the past papers. Okay, so the most simple ones, the easiest one, the ones that I need you all to get the marks for, are the ones that are just how can I put this? That are just, what should I say? The ones that are just numbers, right? Numbers are really intuitive. You just have to ask yourself, is it positive? If it's positive, change the sign. If it's negative, don't change a single thing. That is as simple as it gets. So let me just pull up the question from the 2023 past paper. For those of you who may need to go back for reference, window set equations was what's over here. All right, cool. So we are going to, oh gosh, that's too small. Okay, so you should be, right now, we should be looking at the OneNote page and you should be seeing question 3 and it's an absolute value expression. Okay, if you can't see that, please let me know so I can try and fix that, but you should, that's what we should both be looking at right now. All be looking at right now, rather. All right, cool. So how do you answer this type of expression? We start from the inside always. Always start from the innermost thing, right? As you can see, there's an outside absolute value over here. There's a bracket over here. Then there's an absolute value over here. We're going to start in the middle. In the middle, what do we have? In the middle, we have 2 minus 5. That gives us -3. Is it inside an absolute value expression? Yes, it is. What does that mean? This means that even though it is positive, even though it is negative, the absolute value takes everything that is negative and makes it positive, and everything that is positive, it leaves unchanged. So this was negative, so we have to make it positive. So we're going to treat this -3 as though it were a regular 3. So now we have 2 minus 3, which gives us -1, -1 plus 7. -1 plus 7, oh gosh, 2 minus 3 is -1, that's correct. -1 plus 7 is +8. Okay, the reason why I'm doubting myself is because I'm pretty sure I saw the memo saying that the final answer should be 8. Oh, okay, maybe, okay. Oh, okay, I think I confused myself. Okay, never mind. Let's just proceed. 2 minus 3 plus 7, right? So 2 minus 3 is -1, -1 plus 7 is going to be +8. So I'm going to remove this thing over here, and I'm going to just replace it with a +8. Then I'll ask myself that same question. Is it inside the absolute value? Yes, it is. Is it positive? It is. If it's positive, it just stays unchanged. It does absolutely nothing. Right, so now we're going to have 9 minus 8, and then absolute value. That's going to be equal to, obviously it's going to be equal to the absolute value of 1, but it's inside an absolute value expression. So we have to ask ourselves, is it positive? If so, we leave it unchanged. If it's negative, we make it positive. It is indeed positive, so we're going to make it positive. So we're going to leave it as positive. So that is in essence what that is. So always start from the inside, work your way outwards, and yeah, you should, please don't get those ones wrong. Okay.
Excuse me.
So yes.
With the second calculation, wouldn't it be 6 and not 8? Because -1 plus 7 is 6.
Negatives. Okay. Yeah. Okay. So let me. Oh. Okay. Yes, you're correct. Thank you very much. Because I was so confused as to why the answer is okay. Okay. Yes, you are correct. My apologies. So okay. To trace back a little bit, this should be -3. This is -3 plus. Okay. Oh. Okay. I didn't. Okay. I wasn't looking at this sign over here. That's why. All right, that makes sense now. Okay, thanks a lot, man. Yeah, so this is going to be 2 minus, then this is obviously going to be 3, all right? So that gives us -1 in this particular case, and then -1 plus, okay, this is not correct. So this is -1 plus 7. That's going to give us +6. Something to be careful about is to never use an equal sign when things aren't equal, right? So as you saw over here, I had an equal sign, which I accidentally put, but that doesn't make any mathematical sense. Obviously, this is -1. You can't say -1 is equal to -1 plus 7. So yeah, you can lose marks if you recklessly use an equal sign. So yeah, please make sure that you, okay, what happened? What the hell just happened? Probably press something. Okay, cool. Okay, so yeah, okay, so that's in essence how it works, right? Always work from the inside, work your way outwards, and then work by replacing things as such. If it's already positive, leave it as is. If it's negative, then obviously switch the signs up. Okay, so that's essentially the easy part of absolute values. Now it gets a bit more complicated when you start to deal with absolute value inequalities, because now we have to start to be a little bit more careful. So let me go and get an absolute value inequality. There's essentially 2 types of absolute value inequalities that you can get. All right, you can get, in fact, okay, there really are 3 types. So this one is actually a good way for us to actually talk about all 3 in a single sitting. All right, so we are asked to determine the sets of all x and elements of real numbers such that what. Now, the thing is, these definitions are specifically for when there's only a single absolute value. So how does definition work? The definition works like this. It says that you have a certain expression, right? If I were to say the absolute value, okay, what have I done? I've done the same thing, I think. No, why is it not writing? Oh, okay. All right. So how would I approach this thing over here? There are 2 types of ways an absolute value inequality can be answered. Okay. In fact, let me take a step back. Let's talk about absolute value equations first. So how does an absolute value equation work? You have the absolute value of x plus 3. Obviously, this is a variable, right? So we know that if this value was positive, it would remain unchanged. But if this value was negative, we know we have to change the sign, but we don't know which is which, right? So I'm going to say the absolute value of x plus 3 is equal to 3, right? Remember, this only works if this is positive. So that is a restriction that is absolutely important. So this only works if this is positive, right? So how am I going to do this? Well, this expression could have been equal to 3. Right? This thing over here could have been equal to 3, in which case we knew that we took it and we left it unchanged. But this expression could have also been equal to, give me a second, it's okay, water. Gosh. Okay. It could have also been equal to -3, in which case we knew that the absolute value did its magic and turned the negative answer to positive, right? That is that. So what do we know? Well, if it was equal to 3, then we know to say that x, that is not right. That implies that x would have had to have been equal to 0. This one's pretty straightforward, right? And then in this specific case, for this, then this implies that x is equal to -6. So let me just double check over here. If I were to plug in 0 over here, that's 0 plus 3, that's 3. 3 is equal to 3. Absolutely, 3 is equal to 3, obviously. And then if x is equal to -6, that's -6 plus 3. Therefore, that's obviously going to be equal to 3. That's going to be equal to -3, but it's inside the absolute value, so it's going to be made positive, right? So as a rule, it goes as follows. The absolute value of x is equal to plus or minus a under the condition if and only if and only if a is greater than 0. Okay, that's correct. Okay, so this is how you're going to write it, and this is how we're going to apply it. So always going to be the same. So if I were to say the absolute value of x plus 7 is equal to 4, then you're going to say that x is plus 7 is equal to -4, or x plus 7 is equal to +4. And you solve these, and that's going to be your final answer. If I were to say that the absolute value of x squared plus 4 is equal to +4, let me just say, I'm gonna keep it simple, right? So if I were to say something like 3, right, and then I were to say 1, then we know that x squared plus 3 is equal to -1, or x squared plus 3 is equal to +1. And then we know that to solve for x, we'd have to factorize. So x squared plus 2 is equal to 0, and then x squared plus 2, give me a second. -1 minus 3. No, sorry. Plus, this should be +4. All right. X squared plus 4. And then this should be plus 2 is equal to 0. Right. And what do you guys notice about this? What do you notice about this? So this is a random question I just came up with. But there's something to note about this specific expression. What do you guys notice? Or what do you think I'm trying? What do you think? What is drawing your attention about these specific solutions that I have over here? I am currently looking at the chat, so if you want to type it out, feel free. But I do prefer if you unmute yourselves and say it out loud, so I can hear you and we can discuss. Any brave people? The objective is to solve for x.
Is it just to make sure that you don't take that 4 or that 2 over to the other side and put the square root over it? Because that's obviously wrong.
It is a good idea. A good idea, but that is not what I'm trying to draw to your attention over here, right? The objective is to solve for x in this particular case, right? Obviously, we're trying to solve for x. We're trying to find the x values that will work in this particular case. And you'll notice that it's actually impossible. And look at how these parabolas, not parabolas, these are parabolas. This parabola looks like this. The first parabola looks like this. The other parabola looks also like this, obviously 4 and also 2. We know we factorize. What's the objective of factorizing? The objective behind factorizing is to find the roots. You'll find that because these parabolas are like this, shaped like this and like this, it's impossible for us to hit the x-axis, which means that there are no roots, which means that there are no solutions. So look at the original absolute value expression. You're saying that a certain number squared, right? You're squaring a certain number, which means that already because you're squaring that number, the smallest this can be is 0. So let's assume that's the smallest number they can possibly be, which is 0, right? X squared, the smallest x squared that you can have is 0. Because if you plug in a negative number, that'll be made positive. So you have 0, and then you have 0 plus 3. Right, you'll notice that 0 plus 3 is already past the one that we're looking for, and every other value that you get is already going to be above this one over here. So it's impossible for the absolute value of x squared plus 3 to ever be equal to 1. So this one has no solution, right? Another question where you could actually factorize and solve for x would have solutions. The solutions will be the x values that you find, right? But this specific one has no solution. So that's just something to bear in mind. So yeah, this one has no solutions, but sometimes you'll have solutions. So you just got to be careful about that. So in this specific case, there were no solutions, however. But that's the essence of absolute value equations. Now, absolute value inequalities work a little bit differently. We're running behind time a little bit because I wanted to go through functions. I wanted to go through, what's the thing called? trigonometry, and I wanted to go through derivatives and stuff. So we are a little behind time, and like I have load shedding at 10, so I could hotspot my phone actually. Okay, so maybe if you, oh gosh, my phone it hasn't been charging. Okay, gosh. Okay, my phone hasn't been charging, so I probably can't hotspot. But what was I going to say? Yeah, we're running behind time, so I'm gonna try and be a little bit faster, just so that we can actually cover the essence of trigonometry. I'll probably leave. Okay, I'll leave out the other sections and functions because trig is more important. The others are really just revision. Okay, you'll understand what I mean when you get there. All right. So anyway, to go back to what we have. Oh, God, my phone is wet. Okay, wait. Okay, sorry. Give me a second. Okay, so absolute value inequalities are solved differently from absolute value equations, right? And I want you to just think of it very simply, right? It's not, I don't want you to complicate it. When you see less than, I want you to think in between. And when you see greater than, I want you to think outside of. All right, so remember what we did for equations, right? We knew that it was plus or minus of A. A is still going to be our reference here, but we're going to be in between plus or minus A if it says less than, and then we're going to be outside of plus or minus A if it says greater than. So application-wise, how does that look like? Now we can actually solve this particular thing over here. Okay, so what I was trying to say is that you can notice over here that the definitions are only based off of the following. Let me write the definitions in full. The absolute value of x, to solve for this when it's greater than, let's say greater than A, is going to be equal to, all right, we're going to say the following. This is going to lead to, this is greater than A, right? So we're going to be outside of. So that means that x is going to be outside of negative A, right? And x is going to be on the outside of positive A, right? So I hope that makes sense, right? On a number line, you have negative A and you have positive A. We are on the outside and we're going to be on the outside of negative A, right? So those are the values for A that you could possibly, for x that you could possibly plug in that would allow for the absolute value of x to be greater than A. So then let's consider the alternative where the absolute value of x is less than A. What is that then? In this specific case, we're going to be in between. So x is going to be in between negative A and in between positive A. So what you notice about the definitions over here, the definitions only have a single inequality, a single inequality, right? But the problem that you're given has two. So we're going to make use of our favorite thing and we're going to apply the principle of and. We understand that x plus 1 is expected, the absolute x plus 1 rather, is expected to be greater than or equal to 2, but at the same time, it is expected to be less than or equal to 5. Those are our expectations. So we are going to solve for these individual sets, and then we're going to find their overlap. So to solve for individual sets, this is greater than, so we're going to be on the outside of plus or minus 2. Note that if the A values in any of these cases ever end up being negative, then we know that we can already exclude it, right? So for example, if I were to be careful now, okay, I'll make sure you guys don't make this mistake. If I were to say, when is the absolute value of x plus 2 greater than a negative number, right? This is not no solution. The answer to this is not no solution, right? The answer to this is going to be x in the elements of real numbers. This is saying, when is the absolute value of a number greater than a negative number? An absolute value of a number is always going to be greater than the number. Doesn't matter what x value that you use. That is not the same as asking, when is the absolute value of a number equal to a negative number? You can never have an absolute of a number being equal to a negative number. So that's just something to bear in mind. Don't make that mistake, right? So for the inequalities, you can have a negative, obviously, right? But for the equations, you can never have a negative. A can never be negative, right? Okay, so now let's go back to what we have over here. X plus 1, the absolute x plus 1 has to be greater than or equal to 2, right? And then I can then go as far, I can say that, okay, how would that apply over here, for example? For example, if this was -2, right? If this was -2 and this was like -2, right? Then this would just be, also this would just be x in the elements of real numbers. So this set is already just everything. So we don't need to worry about this set, we need to worry about this. This is going to be the limiting factor. So we're going to be finding the intercepts between an x in the elements of real number sets and an x plus 1 is greater than 5, whatever this ends up being, right? So, but they don't want to make your life easier. So you're probably not going to get this type of question. But just note that if you get that type of a question where they say where one side is negative, then you know that the intercept is just going to rely on the positive one, because the absolute value of a number is always going to be greater than a negative number. There's nothing to solve there because it's always going to be greater. Anyway, let's go back to solving this particular expression. Obviously, there was this was positive. This is positive, so we're going to be on the outside of plus and minus a. In essence, we're going to say x plus 1 is going to be on the outside of this, and x plus 1 is going to be on the outside of that. X is going to be greater than 1, and x is going to be less than -2, -1, -3, right? -1 and 3, right? But then we need to find the intersection of this set on the left, right, with the set on the right. And of course, this one is now going to be the in-between set. So because you can see there's the less sign over here, less than sign. So x plus 1 is going to be in between -5 and in between +5. All right. And then we're going to find the intercept between this set and this set. The intersection, I said intercept, my bad. The intersection, right? So give me a second. All right, so we have -3, just -3, -3, -3, -3, yes. Negative, okay, let me do all of them. We have -5, we have -3, we have 1, and then we have 5, right? So these are all the values that we have over here. If you have a look at what we have, you'll notice, oh gosh, I think I probably messed up the algebra somewhere. Oh, this is, sorry, I haven't finished solving this one. This is going to be x. It's going to be, obviously we're trying to solve for x, right? So that's going to be x is -6, and then we're going to have 5, and 5 minus 1 is going to be 4. Right, so now we have, okay, now it looks nice. So that's going to be -6 over here, and then we're going to have 4 over here. All right, so we're going to draw the first set. The first set is going to be this one over here. As you can see, it's going to be from when x is greater than +1, so from here this way, and then when x is less than -3, so from here, open and open, right? From here this way, right? And then the other one is going to be the in-between set. So specifically between, okay, sorry, I'm messing it up. This is obviously equal to, this is 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 equal to. So really they should be closed. So this should be closed as well. And then we're going to be from -6, that's going to be between -6 and 4. So we essentially have this. Right, now we're looking for the intersection of those two sets, which is going to be, let me just change the color real quick. It's going to be this region over here, inclusive, and this region over here, inclusive, right? So essentially then, x in the elements of -6 up until -3, inclusive, and then we're going to have 1 up until 4, inclusive. And that is that. Are there any questions on that? Going once? Twice? Wrong. Okay. Cool. Okay. So we're running out of time. So I'm going to be a little bit brief. I'm gonna do the question. What question was asked? I think was it Jonathan? Jonathan, yeah. Jonathan asked the question with regards to the triangle inequality. So I'm gonna explain that briefly. If you don't have much time to go too fast on that. So I'm gonna try and explain that on using the 2020 past paper, and then we're gonna talk about trigs, trig, because trig is a pretty thick section, and then we're gonna do the questions regarding yes, trig, but we can do the functions questions as well. So we can do functions questions while we're doing trig. But yeah, with focus points of the functions going to be trig. Okay, so let me just go and grab that question real quick. Sorry, give me a second. The past papers would be in this tab. So 2023, it was the final question in the past paper. I think it was the final question. Sorry, give me a second. Okay, so it was this question. Okay. So the question is as follows. Okay, I'm gonna have to make it smaller because I want to see. I need to look at something for reference. Okay, can I just okay? So it's gonna look a little small. But please bear with me because I need to make sure I look at my notes as well so as not to. Okay, so hopefully that is still visible. If it's not, then please let me know so I can try and see if I can change anything up. But yeah, that should be visible, and in which case we can talk about that. Okay, so what is the triangle inequality first and foremost? Let me just okay. So there are many applications of a triangle inequality. You can use it in the context of like sum of absolute values. You can use it when you're dealing with trigonometric expressions. You can deal with them in vectors. You can deal with them in integrals, but we're going to deal with integrals later on in the semester for this module. And then series and sequences, complex numbers, like triangle inequalities are everywhere, right? But obviously, in this specific where we are right now, you're going to be dealing with them in terms of sum of absolute values and in terms of trigonometric expressions. And later on in the year, you could deal with them in terms of integrals, depending on what we have, the integral thing, right? So the general guideline, if I may, or like how to recognize whether you have to use triangle inequality or not, is they're typically going to be for estimation type questions. So what is estimating? Estimating or like bounding, right? Estimations are, for example, if I say that x is greater than 2, I'm not giving you a specific value for x, right? I'm giving you an estimation of sorts. I'm saying that x could be a number somewhere as long as it's greater than 2, right? It's a number ranging somewhere around there, right? It's an estimation, right? I could bind the numbers a little bit. When you do with integration, you'll find that like you will bind the numbers, for example, from 1 to 3, and then you're going to be integrating a function like x cubed. But don't worry about that right now. Integration can get a little bit scary, so we're gonna keep that on the back for now. For now, what you need to understand is that absolute values, especially when you deal with absolute values with inequalities, and obviously you can use different expressions inside. In this case, they decided to use trigonometric expressions, right? So that's when we're going to use that. Okay, so when you estimating or bounding, whatever, right? If you see absolute values appear, right? If the problem involves absolute values, especially when you have like sums or differences of absolute inside the absolute value. So as you can see over here, there's an absolute value, and inside the absolute value, there's a sum and there's a difference of what, right? We know that in that particular case, we can use our principles of the triangle inequality, right? Also, to break down a complex expression. So a triangle inequality is just a way of rewriting something that you're already given, right? It's just a way of rewriting that thing that you're already given. So if you're going to break down that more complex expression, we're going to use the triangle inequality. So we've taken some time to speak a whole lot, but let us go back and actually speak about the triangle inequality, what the triangle inequality basically states. And again, we don't have time to try to derive and to understand in depth, and I'm not doing any proofs in this session, of course. I'm sure you guys have noticed, but essentially triangle inequality at the core of it all is simple. It goes as follows. Oh gosh. It goes as follows. The absolute value of the sum of two expressions, two functions, essentially, of two functions is going to be less than or equal to the absolute value of the one function plus the absolute value of the other function, right? So how does that relate to in the context of these things over here? These can be rewritten in really a bunch of different ways, but you can really imagine this as a function, and then you are finding the sum of that function with another function, So they could have written this as this, right? So they actually made your life easier, because they could have said 2 sine of x minus root 3 cosine of x, right? They could have said that, but they didn't want to confuse you, because then you may have not seen the triangle inequality here. That's why they said plus and then plus that. So that was essentially their purpose towards doing that, right? So that's why they did that. So if I were to rewrite this expression, then as you can see above here, in terms of whilst applying the triangle inequality, what do I have? Well, first of all, obviously, don't forget what we're trying to solve. Yeah, we're trying to solve for this thing, and we're trying to solve to prove that it's less than or equal to root 12, right? So let's go back to what we have over here. We have the fact that we are going to be, let me think. This expression, this original expression, can be rewritten as a sum. So I can say that this 2 sine of x plus negative root 3 cosine of x has to, oh gosh, cosine of x has to be, and then it has to be less than or equal to the sum of the individual functions that make it up. So what was the first function? The first function was 2 sine of x, right? The absolute value of 2 sine of x. And then the second function was plus, and the second function was, remember they put the negative over there just to make it easier for us to see, right? They put plus, and then but then the thing was still negative. So it's plus, and it's going to be plus negative root 3 cosine of x, right? But we can simplify this a little bit further. We can take the absolute value out. We know that we just have a negative over here. I mean, sorry, this is just a constant. So in terms of a constant, the constants can remain the same. It's a positive constant. It's going to become, can stay 2. But this is a negative constant. We know what the absolute value does. It takes everything that's negative and it makes it positive. So because it's inside the absolute value, this is going to become just positive root 3. So I've just rewritten this thing applying the triangle inequality. This is just step 1 of me applying the triangle inequality. Cool. What is the end objective? I'm trying to prove that it's going to be less than or equal to root 12. Less than or equal to root 12 for all values between negative pi over 3 and pi over 6. That is the end objective. Now, so how does that work in terms of like the goal that we're trying to have over here? What essentially you're trying to do is you're trying to make this triangle inequality, you're trying to manipulate this triangle inequality thing over here such that it ends up looking like root 12. Everything is on the left hand side. Everything on the left hand side is like this, and then that's going to be less than or equal to root 12. That's essentially our end objective. So the next step then is for me to then okay, let me just draw the unit circle, right? So okay, that's trigonometry though. That's trigonometry. Okay, I feel like there's no way for me to go around finishing this problem without explaining trigonometry. So I think we're going to talk about trigonometry. I'm going to give you enough information, and then we're going to come back to this one so that you don't get lost along the way. All right. So trigonometry in this case is straightforward if you understand the basic principle. And the basic principle that I want you to come here with is the fact that every function that you have over here, you need to know your special angles. The special angles are absolutely imperative. If you don't know your special angles, you're not going to be able to manage, right? So I need you to understand your special angles and how they look like. So what are my special angles for this particular section for trigonometry at all? There are going to be 2 triangles, only 2 triangles. If you can memorize these 2 triangles, you're going to be fine. So how do I memorize my triangles? The one triangle is an equilateral, right? Not equilateral. My bad. Isosceles right angle triangle. That's the easiest one to remember. Isosceles right angle triangle. Right? And then the easiest size to remember is going to be 1. Just make them equal to 1. So this is 1, this is 1. Okay, and this is going to be the right angle triangle. So this is an isosceles right angle triangle. This is going to be equal to 1. This is going to be equal to 1. This is easy. You just need to know that this is 1. The equal sides are equal to 1. This, you just use Pythagoras. 1 squared plus 1 squared, square root of that, it's going to be equal to the square root of 2. So this is going to be equal to square root of 2. Pretty straightforward. And then for the other one, you just know it's technically kind of like 1, 2, and 3. But instead of, oh gosh, let me just confirm real quick. Okay, so it's you're technically going 1, 2, and 3, but instead of using 3, we're going to use square root of 3. That's the only difference, right? We're saying 1, 2, and 3, but instead of using 3, we're going to use square root of 3. That's essentially the other triangle. So what does that look like? That's going to be 1, 2, and root 3, right? If you, I'm pretty sure 2 is the biggest one here, right? 2 is the biggest one over here. And again, we're going to still have a right angle triangle. And if 2 is the biggest one over here, by default, it's the it's not the parabola, it's the it's the hypotenuse, right? That leaves us with 1 and root 3. Doesn't matter where you put it. So I'm going to put 1 over here. I'm going to put root 3 over here. Cool. Now I'm left with the final step, right? So these are easy, pretty much, right? So this is 1, 2, and 3, except the 3 is going to be root 3. This is just 1 and 1, and then the final side is going to be easy for us to figure out. They are both right angle triangles. Okay, cool. Now the next portion, I need you guys to understand something very simple. The simple thing is as follows. 360 degrees, the same as 2 pi. Because you're going to deal with these things in terms of radians. 360 degrees is the same as 2 pi. So everything that you want to find is going to be equal to 2 pi. You're gonna make sure you convert it to 2 pi. So I'm going to first deal with it in terms of degrees, then we're going to go to in terms of 2 pi, right? So this is equal to 90 degrees. That means that this is going to be equal to 45 degrees and 45 degrees because the net sum of all the interior angles of a triangle has to add up to 180 degrees, right? So from here, what am I going to do? From here, I'm going to, what am I going to do? Give me a second. Yeah, I'm going to take this 45 degrees. I'm going to convert it then to 2 pi, right? So I'm going to, yeah, and then the rest, yeah. So I'm going to just, let me just come up with the formula for this thing over here. So I know that 360 degrees is equal to pi. I'm going to divide both. No, sorry, that's not right. That's not right. 180 degrees is equal to pi. Therefore, a single degree is equal to pi over 180 degrees. Therefore, if that is that, then if I want 45 degrees, I'm multiplying by 45. I need to multiply this by 45, and that is that, right? So that's basically what you're going to do. So that's 45 divided by 180. That's going to be 1 over 4. In other words, it's going to be pi over 4, right? That's going to be as simple as that, right? So this side over here is going to be equal to pi over 4. This other right angle, remember, this is a right angle triangle, right? And then the other sides that we're going to put are going to be 30 and 60. There's the special angles, right? So this 30, because it's a 30, I would like to put it next to the 3. So you're going to put the one that, because it has a 3, they both have 3. This has a 3, this has a 3. It makes sense to put the 30 right over here, right? That's how I like to remember it. It has a 3, this has a 3, right? And then obviously this means that this remaining one is going to be equal to 60 degrees, right? So that's basically going to be my special triangle. Then again, I'm going to apply the same equation and I'm going to then convert from the one thing to the other thing, right? So in terms of conversion, what am I going to do in this particular case? I'm going to have this, I'm going to multiply it then by multiplied by 30, right? And obviously this is going to be multiplied by 30. So that's going to still be 30 over 180. That gives me 1 over 6. So 30 degrees is going to be equal to pi over 6, in other words, right? So I'm going to just remove this. That's going to be equal to pi over 6 radians. And then we're going to do the same thing for the other guy. That's going to obviously then be, we're going to remove this. It's going to be equal to 60. And it's going to be equal to 60 as well. So again, that's going to be 60 divided by 180. That's obviously a third. So then we know that this other thing is going to be a third of pi. In other words, it's going to be pi over 3. Okay. This is your special. These are your special triangles, and this is all you need to memorize. Okay, for now. For now. All right. Any questions on your special triangles and memorizing them, or anything of that nature? Okay, I'm gonna try and wrap up trigonometry by by 20 past, so that we can spend the last 40 minutes going over derivatives and limits and continuity and stuff. But any questions on that? Special triangles. Okay, now we're going to talk about applications of those special triangles, right? So the application of the special triangles, and okay, what you need to memorize is you need to memorize your double angle identities and your compound angle. Okay, those are the same things. Your Your double angle identities and your half angle identities, essentially, those are things that you need to memorize. Those expressions, you have to memorize them. Otherwise, you're going to be a little bit lost for some of these questions. But let me give you a nice. Let's actually work with the questions now. So let's look at a question like this one, right? These things are supposed to be obtained without a calculator. So we need to expect it to be obtained without a calculator, right? We are given what tan of theta is equal to. This is equal to √3/2. You'll notice that the values √3 and 2 are being used, so we know which special triangle we're going to use, right? We're going to use a special triangle that looks like √3, and it has a 2 over here. So what does this thing say? This thing say, oh no, sorry. Okay, no, this is actually not, it's not that straightforward. It's not that straightforward. √3/2 up over j. Okay, no, it's not that straightforward. Okay, let's yeah, okay. There are two types of questions you could be asked in this type of case. Now, you could be asked a type of question that says something like tan of theta is equal to something, or it could say tan, and then they give you that something is equal to, and then you're trying to find what the ratio is, right? So they could give you the angle, expect you to find the ratio, or they could give you the ratio and expect you to find the angle. So this is where they give you this is what you're doing when they give you the ratio and they expect you to find the angle. Okay, we're not going to be able to deal with functions, unfortunately. Trigonometry is probably going to take the majority of our time right now. But anyway, well, maybe we'll have time. We'll see. Okay, so in this particular case, we're going to say tan of theta is equal to √3/2, right? What does this mean? This means, and I want you to remember, okay, this will help you if you can memorize this, right? Because it's going to be very helpful. Sine of theta is equal to y/x. That's not right. Is equal to y/r. Cos of theta is equal to x/r, and tan of theta is equal to y/x, right? And really, all you need to memorize is these two. If you're too lazy to memorize a third equation, you just need to memorize these two, and then you can just that tan is the same as sine of theta over cos of theta, which is the same as saying y/r divided by x/r, and then you'll find that the r's cancel out and you just left the y/x. So that's if you don't memorize all three of these, but it helps if you can memorize all three of these, right? Also, if you want a simple mnemonic that I was taught back in grade 10 to memorize this, I'm just going to type it real quick. So it was, okay, shield your rear cos x raised tan your exterior, right? So pretty silly, doesn't make much sense, but it helps. So shield, so s sine is equal to y/r, right? Cosine is equal to x/r, and then tan is equal to y/x, right? So that's essentially the basic gist of that. So if I have tan, that gives me y, and that gives me x. I'm looking for sine of theta, however, so I need what r is. So simple, a third equation is going to be x, it's just application of Pythagoras. X squared plus y squared is going to be equal to r squared, right? So that's essentially how simple it is. So, oh, by the way, where does it come from? If you were to draw this from the Cartesian plane, something like this, right? The r is the radial arm. It's always going to be positive. It's the length of that arm, right? That's going to be r over here. This is going to be positive, right? And this is going to be x, and it's going to be positive x in this particular case, right? So this is my x squared plus y squared. You can see that's going to give me r squared, right? So that's essentially where it comes from. Anyway, let's take a step back and let's go back to here, right? So we essentially have x and we have y and we have x, right? Because I can see that in this specific case, I can see that y is clearly equal to √3 and x is clearly equal to 2, right? Because it's saying √3/2. So I can rewrite this then to say that x is equal to 2, y is equal to √3. Therefore, r is equal to the square root of 2 squared plus √3 squared, right? And then I can then solve for that. So the square root of 2 squared, so that's going to be 4 plus 3 really, that's going to give me √7, right? And I'm looking for sine of theta. So if sine of theta is equal to y/r, then sine of theta has to be equal to root 7, no, sorry, that's not right. It has to be equal to, what's y? What's y? Y is root 3. So that's going to be equal to root 3 over r. And r, we found r to be equal to root 7. So root 3 over root 7. And this is going to be my answer. But you need to be particularly careful, right? This is going to be where you may make your initial mistake, right? And that is to pay attention to what they're saying over here. Because over here, if I had just stopped over there, I would get this answer, which is technically a correct answer, but in this specific case, it is the wrong answer. Why is it the wrong answer? Think about what that means in terms of what a ratio means, right? This is tan of theta. This is sine of theta. Where does that come from? Where does the sine of theta come from? It comes from the expression. The full expression is y is equal to sine of theta. It's the different possible y values that we could get from sine of theta. In other words, y is equal to sine of theta is a sine function, right? It's a function that does this and that does this, right? You'll notice that this point over here is going to be obviously the 180 point, which is going to be equal to pi. It's going to be equal to 2 pi. This is going to be equal to 90 degrees. This is going to be equal to 270 degrees, right? So these are going to be our critical values, if you want to put it that way, right? What do you notice about these particular critical values? You'll notice that if we are between, sorry, this is supposed to be, I'm messing it up. This is going to be, if you want to memorize it now, it's just pi over 4. No, sorry. You're counting in terms of pi over 2. So you have 1 pi over 2, you have 2 pi over 2s, you have 3 pi over 2s, and then you have 4 pi over 2s, right? So if you deal with it in terms of like the xy plane, for example, right, something like this, the circle over here, this up here is going to be equal to pi over 2. This is equal to 2 pi over 2, but I'm just going to write it as pi, right? This is equal to 3 pi over 2, and it's equal to 4 pi over 2, which is the same as just saying 2 pi. So that's if you struggle to remember what values to put over here. We're just counting in pi over 2s, right? So anyway, let's go back to this particular thing over here. We found the value over here, right? As you can see, we found it specifically to be equal to root 3 over root 7, but that is specifically only in this region between here and here. Between here and here, you can reach root 3 and over root 7, but think about what's happening in this region as well, right? And think about the sine function. So the sine function over here, the sine function just before over here, it will reach that value of root 3 over root 7. So somewhere over here is going to be root 3 over root 7, but after it reaches its peak and it comes back down again, it's still going to reach another root 3 over root 7. It's going to reach it here, and it's also going to reach it over here. So we need to be careful with regards to which one they're essentially talking about, right? So let's think about it over here in this particular case then. In this particular case, we know that we are going to be dealing between 0 to, this is 0 to pi over 2, but we're interested in pi over 2 to 3 pi over 2. So we're looking for between here and here, right? For this specific example, it technically doesn't really matter per se, but you just need to be careful, right? So why do you need to be careful? You need to be careful because the following. X in this case is equal to 2, right? And x in this case is equal to root 3. But tan is a bit of a weird function because tan, if both tan values, if the root 3, right? If the root 3 were both positive, right? If both of these root 3s were positive, if the root 3 and the 2 were positive, then you get root 3 over 2, right? But look at the x values. So that will be in this quadrant, right? But tan is also, they're both negative in this quadrant as well. So even if you got negative root 3 and negative 2 over here, then you could still get negative root 3 over negative 2, right? That is something to be careful about. So I purposely did the wrong way so that you could see the mistake that you could possibly make, because you could think, oh, damn, I know that's obviously I have the root 3 over here, I can plug it in over here. I have the 2 over here, I can plug it in over here. But that is incorrect. As you can see, as this portion indicates over here, we're specifically between pi over 2 and 3 pi over 2. But tan ends up being positive. So what do we know? We know the cost table, CAST, right? all of them are positive in this table. Only sine is positive in this table, tan is positive in this table, and C is positive in this quadrants, right? So we know the quadrant that we're in is actually this quadrant over here. We are in this specific quadrant. So given that we are in that particular quadrant, what are we going to know about that quadrant? Well, in that specific quadrant, we understand that tan is positive, right? And also this quadrant tan is positive, but we are told that we're between pi over 2 and 3 pi over 2. So we can't use these values. You have to use these values for x, right? That means that x is not actually equal to 2. X is actually equal to -2. As you can see in that quadrant, x is negative. X is not actually equal to y is now actually equal to 3. Root 3 is actually equal to negative root 3, because in this quadrant, y is also going to be negative, and r is always going to be positive, right? So what does that mean then in terms of our actual true sine value? Sine of theta actually is then going to be equal to negative root 3 y over r over root 7, right? In other words, is that? Yeah, okay, yeah. So that can be rewritten then as, let me just fix that real quick, as negative root 3 over root 7, and then this can also be rewritten as negative root 3 over root negative root negative root 3 over 7, right? This is another way to write the exact same expression, and you find that the correct answer is not E, which would be what you would have initially gotten if you had done it the wrong way, but the correct answer would actually be B, the correct way. Any questions on that? Because I know that was a mouthful. That was heavy stuff. I do agree. But are there any? Did I lose someone along the way? What's the consensus here? Okay, cool. Feels like I haven't lost anyone, hopefully. So that's that now. So those are types of questions you could be possibly asked. So you're given a single ratio, and then you ask to determine what the other ratios are with respect to that. So they could then also ask you something like, they give you tan of theta, and then they ask you to then solve for secant theta, right? So, oh gosh, give me a second. Yes, okay, nothing's messing up. Give me a second to unplug and replug. Okay. Also, give me a second. Let me try to recharge my phone because it wasn't charging before because the port was wet. Let me try that again. Okay. Cool. All right. So they could ask you. They could replace the sine of theta with something like secant theta. So instead of saying sine of theta over here, it says. Gosh. It says secant theta. So secant theta. In which case, you're still going to apply the exact same thing, but you know that secant theta is then going to be the reciprocal of cosine, right? There's going to be 1 over cosine of theta. So you just represent it as cosine of theta, and then you just find whatever cosine of theta is, and then you know that you're going to divide 1 by that. So you're going to say 1 divided by whatever cosine of theta is, but you're going to use the exact same approach. You're going to find what x is, and you're going to find what r is, because you know the cosine is going to be equal to x over r, right? And then obviously then you're going to then take that x ratio, whatever, let's say it's going to be equal to negative 4 over 7 for cosine of theta. Remember to find its reciprocal, and then that's going to be 7 over negative 4. So that's kind of like the variation that they could possibly ask you on that. Any questions so far? Okay, cool. All right, so I think we can tackle then a couple of other questions then from the thing pertaining to trigonometry. So give me a second to relocate them real quick. So another question could be, okay. Ooh. Sorry, I'm just gonna. There's not a lot of variety. Okay, this one looks scary. Okay, this one looks scary, so that means it's a good question for us to go through. This is okay. Let me get it first. Okay, so this type of a question is from this was from 2020, so from the 2022 past paper, for those of you who maybe are taking notes for this, and it's one of the latter questions. Let me just give you a specific number. It's specifically question. Okay, I've lost it. It's section C. So at the start of section C. 2022, start of section C. Sorry, let me just 2022, so that's section 3, section C. Okay, cool. So the question that we have is the following, and it's basically a, what's that thing called? A general solutions type. It's similar to general solutions type question. So why do they specify this? X is an element of what? The reason why they find the need to specify this is because of the following. These expressions, these functions are periodic, meaning that after a set amount of time, they're going to start doing the exact same thing that they were doing previously. So the function is doing this, and it goes down, and it's going to do this, and it's going to go down. It's going to go this, it's going to go down. It's going to keep on doing that until infinity. So for them to, okay, how do I put this? Like if they didn't specify X and elements or whatever, then there's no specific X value that you can possibly give, right? Because X could be quite literally anything. So I mean, not anything, obviously, but there's infinite X values because the function can keep on going on and on and on and on and on. So what are the two ways that you can answer an absolute a general solutions question? There are only two ways that you can answer this one, right? So the first way is to write in terms of a single trig ratio first, right? What do I mean by that? Let's say the question said sine of x is equal to cosine of x, right? And then this is it, right? So they said solve for x when sine of x is equal to cosine of x. This is literally all they give you. I can rewrite this in terms of a single trigonometric ratio. I can divide both sides by cosine of x. That gives me tan of x is equal to 1, right? And then now I'm trying to find all instances where tan of x is equal to 1, right? And you'll notice from your special triangle that did pi over 4 and pi over 4, when is tan of x equal to 1? Well, this is 1, this is 1, this is going to be root 2, right? I'm going to say opposite over adjacent. So tan of x is equal to 1. The first time tan of x is equal to 1 is when pi over 4 is equal to 1. So tan of pi over 4 is equal to 1. It's important, absolutely imperative that you find the links between these three things. The special triangles, right? You find the link between that and the unit circle and the graphs themselves. So what I'm going to do is I am making videos for these and they'll be done by the end of recess. So in case you don't understand like any of this, like you can probably like study that, but this is beyond the scope of this specific section because then we'd be here forever. But these are things based on what I've already given you, you can actually explore these already on your own, right? So do try to explore these on your own. You'll notice that the values never surpass 1 and -1 and -1 and 1. That's because the unit circle, it's in its name, has a length of 1. The radius is equal to 1, right? You'll notice that the highest value that you ever get over here is equal to 1 and equal to -1 over here. You'll notice that when you find your trigonometric ratios for any of the special triangles, you're only going to be positive, and it's going to be between 0 to 1. So I need you to understand the links between all three of these. These are things that you can experiment on your own. I would advise you to do it on your own, because what you figure out on your own, you're gonna most likely never forget. But I am also going to the videos I'm making are actually explaining like exactly how you could figure them out on your own as well. I mean, sorry, I explain them, but yeah, anyway, that's besides the point. Let's go back to where we're at right now. So this is tan of pi over 4 is equal to 1, right? So we know that, which means that a solution for this is going to be pi over 4. But the function is going to start doing the exact same thing, right? Well, how does a tan function look like? A tan function looks like this. It's going to do this. It's going to hit this thing over here, right? This is half of its period, right? A full period of a tan function is equal to pi, right? So if this is half of a period, then this is really just pi over 2. Then from here, we're going to have a full period like this, right? So really we're saying pi over 2 plus pi, which is the same as plus 2 pi over 2, which is the same as saying 3 pi over 2. 1 pi over 2 plus 2 pi over 2 equals 3 pi over 2. It's going to be equal to 3 pi over 2, right? So what did we find out over here? We found out that when we have pi over 4, so somewhere in the middle over here, pi over 4, right? We have a value of 1. But pi degrees later, after the thing has done a full period, we are exactly at 1 again. And then again, if you add pi again, you can still be at 1. And this happens on both sides. So how do we represent that mathematically? Mathematically, we say the following. We say tan of theta or x is equal to 1, right? Therefore, we have our special reference angle. So theta is equal to pi over 4. That's the first instance of that. But we know that that can continue forever. So we can say plus, and then they sometimes use n, they sometimes use k. I'll use n this time. Plus n multiplied by, and I'm going to use the period, right? To complete a full period is going to be equal to pi, right? Full period is going to take pi to complete, right? So n multiplied by pi, right? And that's going to be the full period. And then I'm going to specifically say that n is an element of integers. That is important because you are saying that you're going to add exactly 1 pi after that, then 2 pi or negative pi or negative 2 pi. You can't add like negative √3 of pi or whatever. You have to add a whole pi or minus a whole pi, right? Because as you can see over here, we're jumping from pi over 4. We are adding a full pi. We are adding a full pi. We are adding a full pi or subtracting a full pi, regardless of whether you're going to left or to the right, right? The point is we have to make sure you're saying that it's an element of integers. That's a very important part of the expression. Okay, now to go back to where am I going back to? To go back to here, right? So this is sine of x over cosine of x is equal to cosine of x over cosine of x, and that's going to be tan of x is equal to 1. Cool, we have that sort done and dusted, right? And then this is going to be your final answer. This is your final answer as it is. But if I were then to specify that specifically between negative pi over 3 and pi over 2, then I'm gonna plug in n values, right? I'm gonna plug in n values, and I'm gonna say, for example, pi over 4 plus 1 pi or whatever, and I'm gonna just find the n values that will result in theta being between the bounds that they give me. That's essentially the objective over here. So that's the one way where you try to write in terms of a single trigonometric ratio, and the second way is where you factorize. Where you can't write in terms of a single trigonometric ratio, you're going to have to factorize. And that's actually the way that's going to be needed for this specific problem. So bearing that in mind, let us actually try to solve this specific problem, because this is obviously a factorizing type example. So if you can't write in terms of a single trigonometric ratio, then the thing that you have to do is you have to factorize. But you have to be really careful because you have to manipulate the equations and write it as best as you can, right? And factorize always, you have to set it equal to 0. That's always the rule of thumb for factorizing, right? So again, it's typically not ideal to use too many trigonometric ratios. You're trying to reduce as many trigonometric ratios as possible, but tan is a really obscure one. So instead of using tan, it makes sense for me to use sine of x over cosine of x, right? So that's what I'm going to do. I'm going to say 3 sine of x over cosine of x, and that's going to be like my reference or whatever. By the way, I mentioned that I want to do a triangle inequality type problem. I probably won't have time. We're going to run out of time. Yeah, so what I'm going to do is like tomorrow early morning, because I won't have time tonight because I have load shedding and stuff. I'm going to record the video. I'm going to send you guys a video. So again, I don't want to spam like the whatever group chats, whatever. So check again, like I'll announce exactly the specific details on the group chat, so please be sure to what's okay. But anyway, to proceed with where we were, I'm going to write this, and this is going to be 3 sine of x over cosine of x, right? The objective now is we could, okay, you would I know that you can't do what, you can't I personally know that you can't give me a second. I know that you can't write this in terms of a single trigonometric ratio, so that's why I'm factorizing, right? That's going to be equal to 2 on the right hand side, and then it's not nice to really have I'd rather prefer to just have x by itself, right? Why do I want x by itself? Just because this is x and this is x, and it would be nice to have this as x as well. If this was 2x, then that would be a different story. There's no need really to worry too much, right? Because they're both 2x, so this could be 2x, this could be 2x. But it's better to have it in terms of even the angle should be the same. So the angle that I'm going to try and write is going to be in terms of x. So, and this is what you need to memorize. You need to know the double angle identity. So this is going to be when you say sine of 2x, that's the same as saying sine of x over cosine of x. That's something you have to. Oh gosh, don't shoot me, don't shoot me. Okay, that is not right. That is the same as saying 2 sine of x cosine of x, right? This is a double angle identity, which is derived from the compound angle identity. But I haven't really seen much compound angle identity type questions. Also, going to take too much time to try and teach that. So this is just a double angle identity. Also know the 3 forms of the cosine one, right? So the cosine one is cosine 2x is going to be equal to cosine what's x, right, minus sine x, right? And then the other 3 ways just basically come from this. Sine of x squared plus cos of squared is equal to 1. This is another thing you have to memorize, right? This is another equation. So one way is where you write it in terms of sine. So you can say cos of 2x whatever is equal to excuse me, 1 minus sine of x squared or whatever, right? Then where basically you take this cos squared x whatever, you replace it with this, right? And then the other ones where you make sine that substitute formula, and then you're going to say is equal to 1 minus cosine whatever, and then you plug those into the formula as well, right? So once you derive those, the three versions of this thing is going to be 2 cosine theta, well x really, but minus sine minus 1, and then 1 minus 2 sine theta, right? So just these are things to memorize. But for this specific problem, we obviously need the 2 sine of x cosine of x what. So that's what I'm going to do over here. So in this case, I have 2, right? And I'm going to apply the double angle identity. That's going to be 2 sine of x cosine of x, because there are 2 x's. Cosine of x. That's going to be equal to 4 sine of x cosine of x. So far, so good. All right. Where do you go from here? Well, again, the end objective is to try to factorize, because we tried to write in terms of a single trigonometric ratio. That was not possible. So if you can't write in terms of a single trigonometric ratio, the next thing to do is to try to factorize. So that's what I'm doing right now. I'm going to try and factorize. So how am I going to factorize this particular expression? Well, I'm going to multiply both sides by cosine of x. So this is going to be 3 sine of x is equal to, and I'm going to have excuse me, sorry, give me a second. I'm going to have, okay, 3 sine of x is going to be equal to, and then I'm going to have, let me think, mathematically, I'm multiplying by x, what's what? So that should be 4 sine of x cosine, like this, right? I'm multiplying both sides by cosine of x, right? So I basically have this, right? And then now I know that I need to try to factorize this somehow. So if you need to factorize, we bring everything to a single side. That's going to be 3 sine of x minus 4 sine of x cosine x is equal to 0. In this particular case, I can take sine of x out as a HCF, highest common factor. That's sine of x. That gives me 3 minus 4 cosine x is equal to 0. Then I can basically deal with these as their own general solutions, right? So now I can separate them as follows. I can say then sine of x is equal to 0, or 3 minus 4 cosine x is equal to 0. See, these things build up. Yeah? The whole or thing, the whole factorizing sitting equal to 0, you'll see it everywhere. So when is sine of x equal to 0? That one's pretty straightforward. So I'm going to look at the sine function as follows. As you can see over here, I have, it does this, goes up here, it goes down over here, right? When is it equal to 0? It's equal to 0 over here, it's equal to 0 over here, it's equal to 0 over here. This is pretty straightforward. So it's going to be equal to 0 at 0, at pi, at 2 pi, right? And obviously in this other direction, it's going to be equal to 0 at against every pi, right? So it's going to be negative pi, negative 2 pi, whatever, right? So let's look at what we're actually given over here. We are interested specifically between 0 and pi. So which solutions are we going to take then? Well, the solution that we can take is 0 and pi, because those are the only ones that are within the restriction that we're given, right? Otherwise, it could have been, the full solution is as follows. X is equal to, we take a reference, which is going to be 0, 0 plus, and then we know that it's happening every pi, right? So we know that that's happening 0 plus every pi, right? Multiplied by n, where n is an element of integers. But because we actually given specific boundaries, this is not the final answer. The final answer will be x is an element of, really, I can say x is equal to, I'm writing in terms of this thing over here, 0 and pi. So these are the values for x based off of the first side. Then we'll do the same thing for the values of x, but now based off of the other side over here. So how am I going to do this side over here? Well, I'm going to say cosine x is going to be equal to, let me think, -3, but I'm going to divide by -4. So it's just going to be 3 over 4, but I need to know what cosine of x is. So cosine of x is going to be equal to √3. Let me think. Yeah, √3 over 2, right? Now you need to understand the following. That it could have been really, when you're saying the square roots of something, it could be plus or minus, right? It could be plus or it could be minus. But let's think about what that means in terms of like the question that we were given itself. So in the question that we're given itself, we know that we're interested between 0 and pi. So let's look at what the function is doing between 0 and pi. So there we are. This is 0, right? This is going to be pi over 2, and this is going to be equal to pi, right? That's going to be equal to pi, right? So what does this basically mean in terms of what we have over here? We're looking for when the graph is equal to either √3 over 2, right? Or when the graph is equal to -√3 over 2, because if I were to find the square root of cosine x squared, I could have gotten plus √3 over 2, or I could have gotten -√3 over 2. What does that basically mean then in the context of what I have over here? Well, √3 over 2, when do you have √3 over 2? This is where special triangles again come into play. You know which triangle that is going to be. Of course, the triangle with the √3, and because it's the √3, it's going to have pi over 6 over here, and it's going to be pi over 3, I do believe. And then here is going to be the 1, so we know 1, 2, and 3, right? 1, 2, 3. All right, cool. So now, which one is this over here? If you have a look over here, we have √3 over 2. So as you can see, √3 over 2 is opposite. No. Cosine. Cosine is adjacent. So adjacent over hypotenuse. Adjacent over hypotenuse, yes. √3 over 2 comes from adjacent over hypotenuse. So the reference angle that we can use is going to be pi over 6. So I'm going to use pi over 6 as my reference angle. So my reference angle is going to be pi over 6. So x is going to be equal to pi over 6, right? And then that's going to be plus, what? That's going to be plus, again, same thing, because it's periodic, it's going to happen every pi. So every every full period now. So that's going to be n multiplied by 2 pi, right? Every full period. Now I want to explain like the way this comes from, because the other one was a bit straightforward. It was just a simple sign, so you didn't really see where this came from in its entirety. Because the other version is also going to be x is equal to, and I want to say negative pi over 6. I want to say plus. No, sorry, that's not right. No, that's not right. I will explain exactly what this means just now. But it would be, the other one would be, the other reference angle is going to be, let me just, sorry, let me think about this. Pi over 6, I'll be pi minus pi over 6, yeah. The other one's going to be pi minus pi over 6, right? And then also, plus n times 2 pi. Okay, now let me explain where that comes into play and why we technically did it for this one as well, but it's just because, okay. let me take a step back. Let me explain where this comes from. We have the sine function, right? The sine function does this, right? After every period, so let's say I took this point as a reference, right? If I added exactly a full period to that, I would be exactly where I started. I'll be over here, except I'll be a full period afterwards. We know that sine repeats after every 2 pi. So is it 2 pi? After every 2 pi. So yes. So this would be exactly where it was over here as well. But this point is also this same point over here, the same point, the same y value, right? Sine of theta, right, which is a y value, is also reached over here. It's also reached over here. It's also reached over here. It's also reached over here, right? So it's reached on both sides, reached on the left-hand side of the peak and also on the right-hand side of the peak, right? So how do you get to that? It's going to be really, really simple. You're just going to have two reference angles. So when you have like, if I were to say sine of theta is equal to, let's say I said it's equal to a half, something like a half, right? How do I write this? I would say theta is equal to, and then I would let me deal with it in terms of degrees. So shift sine, of course, I'm just using a calculator, but you have to use your special triangles over here. So shift sine of a half. We know that the reference angle, the first reference angle, the easiest reference angle is going to be 30 degrees, right? And then how do you find the second reference angle? So let me first finish this one. So that's going to be 30 degrees plus, and then we know after every pi, it's going to do the exact same thing. So plus, I'm going to add exactly pi multiplied by n, right? Sorry, not pi, 2 pi. Every 2 pi is going to do the exact same thing, right? After every 2 pi, right? Then I'm going to use this reference angle, the same reference angle, to do the other one. So the other version, the other side is going to be theta is equal to, and then I hope you guys remember, but sine of 180 degrees minus theta is the same as sine of theta. So in the context of this one, I'm really saying sine of 180 degrees minus theta is the same as theta. So this is also going to be equal to sine is going to be equal to obviously 150 degrees, right? So this is the second reference angle. So 150 degrees plus 2 pi multiplied by n. Remember that n is an element of integers. Cool. So those are our two reference angles. We do the exact same thing for sine. We do the exact same thing for cosine, right? Because in a single period, you reach the same values twice, right? The value that you reach over here, you can reach over here. The value you reach over here, you can reach over here. The reason why we don't do that with tan is because tan only reaches a certain value once in a period, right? Tan does this. Every value is touched once, then it goes on to its next period. Touch once, goes on to its next period. Touch once, goes on to the next period, right? Cosine as well, do the exact same thing. So you have our reference angle of pi over 6, right? And then we're going to do it again also in relative to pi. So it's still going to be pi minus pi over 6, right? Why do I say relative to pi? We use 180 degrees over here, right? So you're going to use 180 degrees basically over here as well, right? So it's basically the exact same thing. So yeah, really similar idea, right? So okay, wait, no, sorry. There's a slight wait. Let me just cosine. Cosine is slightly different because cosine of 180 degrees minus theta is equal to negative cosine of theta, right? Again, this is something you should remember from high school. So in reference to this one, then we're going to basically be doing 180 degrees minus theta, and then we need to make the whole thing negative after that. But yeah, don't need to worry too much about that. That's yeah. Okay. Anyway, in essence, then we have the following. Yeah? We have the fact that we can use pi over 6 as our reference angle, or we could use pi minus pi over 6 is our other reference angle, right? And then if you do your calculations and you add your n's and whatever, you'll find that the values you can only get that is within the range that they gave us. They specify that we can only be between 0 and pi. So when you mess around with the different n values that you could possibly have, you'll find that 0 and pi are the only values that are going to work, and also pi over 6 and pi minus pi over 6, or the other is the other value that can work, pi minus pi over 6. So these are the two values on this side, and then you also have two values on the other side over here, right? So therefore, the full solution set would be then equal to x is going to be equal to 0 pi over 6, 5 pi over 6 if you simplify pi minus pi over 6, and then you also have pi, right? So that's essentially how you'd answer that type of a question. Are there any questions on that? Cool. All right. So we are running a little late for time because this is the time I was supposed to finish with the trig with trig. Let me think. Trig. Yeah. So we need to wrap up limits, continuity, and derivatives in 30 minutes because I have load shedding and they're really strict. Like exactly half past is I'm not half past at exactly o'clock that the electricity is going to disappear. So if you have any questions, just ask in the group chat. Specifically the group chat link that's Joel, because I can answer them questions from there from my phone, but I won't be able to continue the meeting. That's if it suddenly cuts off and I'm not like aware of the time, that's the reason why. Right. So the final thing we're going to go on to now is going to be limits, continuity, and what. All right. Can I just ask for reference, because I'm not too sure. Have you guys done the squeeze theorem or the sandwich method? They have different names. I don't know if you guys are familiar with that method of. I do see in the past paper, but I don't remember if you all did it like in the tats and stuff if you did in class, whatever. Does if I say squeeze theorem, whatever, does that ring a bell to anyone? All right. I'm going to just continue then, and yeah, because squeeze theorem is it's a bit of a mouthful. I know. I feel like if I try to cover it right now, it might not be optimal. Yes.
Will you have time to go through the chain rule?
The channel that I'm trying my best to push for that. So I'm
Okay,
gonna spend
thank
like
you.
10 minutes or whatever on this thing, and I'm gonna do derivatives and stuff. Yeah. So
Okay, cool. Thank you.
no problem.
Thanks.
All right. So cool. Okay. So you asked to find the limits as x approaches 3. Okay. Like let me take a step back. Let's talk about limits first. Okay. So I'm gonna be brushing through this really quickly. So like within 10 minutes, I'm gonna try and finish the limits now. All right. So we have this. You have a particular function. Let's say the function does this. Okay, it keeps on thinking I'm trying to like scratch it out, whatever. So you have a function, and let's say the function does this, and it does this, and it does this, whatever. Let's say it does this, whatever. Okay, and then let's say it does this, and then let's say it does this, it does that, and then let's say it does. Okay, so this is. I don't do that. Let me. Okay, I'm trying to do like all the different types of continuity. Okay, I'm gonna say this. I'm gonna say this, and I'm gonna say this. I'm gonna say this. The keyword that you're always going to see when you talk about limits is the keyword approaching. So, what is a limit? What is a limit? A full limit. So there's a left-hand limit and there's a right-hand limit, and then there's a limit itself. When you see the word limit, we're talking about both sides. What do I mean by both sides? If you have a look at this specific, let's look. In fact, let me do this, right? So the limit is typically as we're approaching a specific x value, right? There's also you also get okay. Let me not confuse you like infinite limits and limits to infinity. But for now, you need to understand that like a limit, like if I were to say, let's say we're talking about approaching this specific thing over here, right? So this x value, let's say that's going to be equal to like 10 or something, right? And let's say I'm asking for the limits as x approaches 10 for this function. I'm going to call it f of x, right? Because obviously it's a function made up of pieces of other functions. It's a piecewise function, right? So you see that this is equal to 5 over here. We're looking for the limits as the x values approach 10. What do you note from there? As we're approaching 10, you'll find that we are actually approaching 5 from the left-hand side of 10 and from the right-hand side of 10. So the limit exists and the limit is equal to 5. Right, because if you're approaching the same value from the left-hand side and the right-hand side, again, approaching, it's going to exist, right? Whether it is open or whether it is closed, we are approaching, we are getting closer to the same value. Cool. Let's have a look at what's happening over here. So let's assume I didn't make it that distinct, but let's make it a bit more distinct. Let's say it does this. and then it does that, right? So it's doing something like this, right? And then I'm looking for the limits as we're approaching a value like 4. If I approach the value of 4 from the left-hand side, I'm using this function. I'm approaching 4 from left-hand side. You'll find that I end up being equal to whatever this value is. Like let's call it like -10, for example. But from the right-hand side, I'm actually equal to like -5, for example. So the limit as x approaches 10 for the function is equal to, well, in fact, does not exist because you're approaching different values from the left-hand side and from the right-hand side. Again, let's look at it from this perspective. Let's say as we're approaching whatever this value is over here, from the left-hand side, we're getting closer to positive infinity. From the right-hand side, we're approaching negative infinity. We're not approaching the same infinity. If you're approaching the same infinity, again, the limit does not exist. But if they're both approaching positive infinity, then the limit is positive infinity. So what is the limit? What is the limit in essence? A limit is a y value that the function approaches as we get closer from the left and to the right to a specific x value. In essence, that's really what a limit is, right? But sometimes they may ask you for left-hand limits. So just if it's left-hand limits, then they'll say something like this, which is interested in what we're approaching from the left-hand side and what we're approaching from the right-hand side. So a left-hand limit and a right-hand limit could exist, right? But the limit for the entire function might not exist. Cool, that is a limit. Now we're going to talk about why we have all these fancy expressions. Wait, could you guys actually see my thing? I hope you guys can see my thing. Yes, you could. Okay, cool. All right, so that's basically what a limit is now. So now let's talk about continuity, because continuity just means, can you draw this function without lifting your pen? If you can draw a function without lifting your pen, the function is continuous. So in other words, okay, I'm saying function, but really, oftentimes they'll tell you a portion of a function. Is a function continuous at 2? Is a function continuous at 4? Right? So when you reach 2, do you have to lift your pen, or do you stay at a point, right? So let's say something, for example, let's say the function does this, and then the function does this, and it does this, and then it jumps to here, and it does this, and then it goes to infinity here, and then it continues here, whatever, right? And then they're looking for the, they're asking you, is the function continuous at 5, right? Don't think, oh, because you see some gaps at different places, that means that the function is not continuous at 5. No. This means that when you're reaching 5 from the left and from the right, do you have to lift your pen up? If you don't have to lift your pen up, then the function is continuous. Even though there are discontinuities in other different places, the function specifically at 5 is going to be continuous. So let's look at what's happening specifically at 5. From the left-hand side, we are approaching a specific value. From the right-hand side, we're approaching a specific value, and we're not lifting up our pen, which means that the function actually exists at that specific point, which means that a function is continuous if, and only if, the limit as x approaches a from the left-hand side is equal, for the function f of x is equal to L, and the limit as x approaches a from the right-hand side of the function is equal to L, as in we're approaching the exact same value from the left and from the right. And the most important part to say that we don't lift our pen is that f of x is equal to, sorry, f of a specifically. Like if you actually plug in that a value itself, right, is also equal to L, right? Because what could happen is the following, right? You could have a limit. You could be approaching the exact same value, right? You could be approaching the exact same value at this particular thing. So let me just resketch it real quick. You could be approaching the exact same value from the left and from the right. So there's a function over here, but then, okay, I messed it up. Okay, so we could be approaching the exact same value from the left and from the right, and then there's a gap over here, and then the function continues, and then it's over here. Over here, it's defined over here. So what does that mean over here? From the left-hand side, the limit is the same because you're approaching the same value. From the right-hand side, the limit is the same because you're approaching the same value. But we're not continuous because specifically at that specific point, f of a is not equal to L, is not equal to L. So because f of a is not equal to L, the function is not going to be continuous, and it's going to be a jump discontinuity, right? And no, that's not right. That's not right. That's a removable discontinuity, right? And then how do you get a jump discontinuity? A jump discontinuity is as follows. You're coming from the left-hand side, right? the limit from the left-hand side is not equal to the limit from the right-hand side. So you don't even have to check that, you don't even need to check that where you define specifically there. As long as the limit from the left-hand side is not equal to the limit from the right-hand side and defines you somewhere random or somewhere here or whatever, there's going to be a jump discontinuity. And then a infinite discontinuity is just basically where the limit from either side, whether it's the left or from the right, goes up until positive or negative infinity. That's going to be a infinite discontinuity. So those are the three types of discontinuities that you can have. Visually speaking, a jump discontinuity is if you're sketching a function, you have to jump to something somewhere else, then that's a jump discontinuity. If you're sketching a function and you have to like lift your finger briefly before you can continue, that's going to be a there's going to be a removable discontinuity. And if you're sketching and you see that you're going all the way up until infinity over here, that's going to be an infinite discontinuity. So those are the three types of discontinuities that you could possibly get and how you can calculate those discontinuities. Now, you're not always going to be given a pretty graph, however, so we have to resort to other methods to calculate our limits. So let us deal with a limit expression, our limit equation now, after I've explained the basic principle. Okay, I'm gonna have to try and be quick now. How much time do I have for this really? Okay, I'm gonna try and be, oh gosh, 5 minutes. I'm gonna try and do limits in 5 minutes, and then we're going to go to derivatives and like equations of the tangents, what's. Okay, so this is the function this is the thing that we have over here. It doesn't hurt to check, but I will tell you right now that most of the time they don't like you and they don't want to make your life easier. But let's just check just in case now. Let's have a look in this particular case. In this particular case, we can check as follows. The limit of as x approaches 3 for this particular function. First of all, can we even plug in 3 first and foremost? Well, you'll find that you can't really plug in 3, right? If you plug in 3, the denominator is going to be equal to 0. Okay, let me just check. 9 minus 2 times 3. So that's 9 minus 6 minus 3, right? It doesn't hurt to check. If you can plug the limit directly, then that's really just a free mark over there. But unfortunately, we can't plug in the limit directly, right? The second thing that you could do is use L'Hopital's rule. So L'Hopital's rule is basically a principle that helps you to calculate limits. Not always applicable, but sometimes it will work. So in this particular case, what does L'Hopital rule basically tell us that we can do? It tells us that if the numerator, and it's often helpful if like the numerator, let's say this thing is like 3, the way the highest degree is not the same thing, right? So let's say the numerator over here is going to be equal to like 3, and over here it's equal to 2, right? What do? You differentiate the numerator and the denominator, and then you're going to keep on differentiating until you can plug in the value safely. So the first step of L'Hopital will be like limit as x approaches 3, and that's going to be 2x minus 2 minus 15 over 2x minus 2. Sorry, not minus 15. Obviously, 15 falls away when you find the derivative, right? And then if you can plug in 3 in this specific expression, then the limit over here would exist. Wait, let me actually check. I was quick to dismiss 2x minus 2, 2x minus, let me see, 2x minus 2, and then can I plug in 3? So I'll be 2 times 3 minus 2 over 2 times 3, 2x minus 2 minus 2. So it's going to be, okay, I don't know why they're saying limit doesn't exist. 6 minus 2, that's going to be 6, unless I differentiated wrong. 6 minus 2 over 6 minus 2. Okay, I'm probably making a mistake somewhere. Let me think. X squared minus 2x minus 15 over x squared. That's 2x minus 2. That's 2x minus. That's the same thing. 2x minus 2. Okay. Okay. But for all intents and purposes, L'Hopital's rule is typically going to be used. In fact, let me first. I'm just gonna make a note of just double checking that because typically it should be something that should work. And the answer should work if you like differentiate the numerator and denominator, right? Sometimes it's hard to like do there's like fancy algebra that you can do to try and figure out like what the limit is, but unfortunately for this specific case, it's kind of difficult for us to try to figure that out. But anyway, let's try and understand what happens in this specific case. Now, what are they doing over here? First of all, in the numerator, if you were to plug in 3, you get a positive value. You get a value specific that's equal to negative 12, right? So in numerator, we have negative 12. Now, what's happening in the denominator? Well, if you plug in a value of 3, then you're approaching infinity, of course. But let's think about specifically what happens from the left-hand side and from the right-hand side, right? This is going to be a number like negative 12. Let's think about what happens when you're plugging in 3 from the left-hand side. So you're going to be approaching 0, true, right? And you're going to have negative 12 divided by like a really, 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 really small number, right? The number is going to get closer to 0, right? The smaller the number, the closer to infinity we're going to get, right? But if we're coming in from the right-hand side, right? If we're coming from the right-hand side, imagine you're coming from the right-hand side of infinity. What happens over here? Let's think about a number that is from the right-hand side of this thing over here. So let's think of a number like 4. So a number like 4 gives us 4 squared minus 2 times 4 minus 3. That's going to give us 16 minus 8 minus 3. 16 minus 8 is 8. 8 minus 3 is going to be equal to 5, right? So that's going to be equal to 5. That's going to be positive, which means that 4 is from the right-hand side. So the limit coming from the right-hand side is positive, right? So essentially you have negative 12 being divided by a really, 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 really small positive number, right? Which means that the final answer for this one from the right-hand side, the limit from the right-hand side is going to be equal to negative infinity, right? Because you have a negative number divided by a really, really small positive number. That's going to give you a really, really big number, specifically negative infinity. But what if I have negative 12 divided by a really, really, really small negative number? So let me try and check something like, for example, negative, let me try and plug in a number from the right-hand side of 3. So a number like 2. So that's going to be like 2 squared. It's going to be 4 minus 2 times 2. That's going to be 2 times 2. That's going to be 4 as well. 4 minus 3, I think. 4 minus 3. 4 minus 3 minus 3. That's going to be 4 minus 4. It's going to be 0. 0 minus 3. That's going to be equal to negative 3. So that's going to be a negative number. So you're dividing negative 12 by a really, really small negative number, right? Something really, really small with negative number, which means that you're going to be approaching positive infinity from the left-hand side. So the limit from the left-hand side, it gives you positive infinity, and from the right-hand side gives you negative infinity. It's not the same infinity, and because it's not the same infinity, the limit cannot exist. If you're approaching different values from the left than you're approaching from the right, the limit cannot exist. So I'm just going to go through 2 methods of manipulating an expression because we're running out of time to answer limit type questions. The one way is for regular algebra type questions, and then the other way, again, L'Hopital's rule really comes in clutch when you know how to differentiate. So once you know how to differentiate, please only use L'Hopital's rule. That's going to save you a whole lot of time. But for now, we're going to just use you can use the methods that we do know. All right. So this is a nice problem for us to speak of limits. So let me just take this one, and then I'm going to cover this one real quick, and we're going to do one for trigonometry. So this one, how do you approach this type of a problem? This type of a problem is as follows now. And the problem is going to be evaluated as follows. Let me think. Okay, whenever you have something like this, an algebra type problem, first of all, it's an absolute value type problem. Make sure that you actually account for the 2 different absolute value expressions, right? We know that this thing could be equal to x and completely unchanged, right? It just remains completely unchanged, or it could be negative of what it is, right? We need to account for both of those instances. So make sure that you account for both instances so that you can drop the absolute value symbol, right? But be careful over here, right? So we're not actually going to account for both instances in this case because we're actually approaching a specific value, right? So this is root x, and we are approaching -1. So think about it. You're approaching -1, which means that you're approaching -1 over here. You're using this side of the absolute value function. Does that make sense, right? We're coming from the left-hand side, we're approaching -1. From the left-hand side and from the right-hand side, you are right on this side of the absolute value expression. So you can't use this equation. You can't use the full absolute value. You can't use this side over here. You're specifically only interested in this single absolute value side over here because that's the side that has -1. So that's why you see over here, they have negative x over here, right? So that's 1 minus negative x. That's obviously can be simplified as 1 plus x. Cool. Where from here? From here, we're going to find every time we have a square root, wherever you have a square root and you have another symbol over here. So let's say if it says like 2 minus square root, whatever. If it says square root of 3, let's say square root of 3 minus x, what's plus 2 whatever, you're going to multiply by 1, but specifically the conjugate of the term with the square root. What does that mean? A conjugate basically just means that when you have two expressions, you change the middle sign to the opposite sign. So in this case, the middle sign is negative, so you're going to multiply by the opposite sign over there. But you're going to multiply by 1, right? Because you can't change the original expression. So we're multiplying by 1, which is 2 plus root 3 over 6 over 2 plus root 3 over 6. Root 3 minus 6 rather, right? And then you just multiply that out. Obviously, then that's going to be a difference of squares. So it's going to be, you multiply the 4 and it's going to be minus, and you can multiply the things with each other. Obviously, then that means the square root falls away and you just left with this, right? Why did we do that? We did that because when you tried to plug in -1, we ended up having something like 1 plus -1, which obviously was something we can't have. So that's just one way to manipulate the expression. And then we manipulate the expression. The rest is algebra with the end objective to simplify it as follows: 1 over 4. Because now once we manipulate the expression by multiplying by the conjugates, we could actually now plug in plug in -1 without a problem, right? And then so plug in -1 without a problem. What else I want to say? By the way, if I do break away for like a second, like if it's the o'clock, I do want to actually cover derivatives properly. My phone is at 20%, so I will hotspot my phone. So I'll hotspot myself from my phone. So I'll rejoin as soon as the Wi-Fi kicks me out, just so I can just finish derivatives properly. Anyway, let's have a look at this expression real quick. Let me think. Okay, yeah. So this is it, right? So that's this type of a limit question. And then another common, so these are the two types of common really limit type questions that you could possibly get. So the second common limit question is one whereby you have a trig. You have trig, right? So let me pull it out real quick. And this is just something that you have to know. Right? And what is it that you have to know? Whenever you have a trig, most of the time, what they want you to do is to apply the principle that the limit as x approaches 0 for sine of x over x is equal to 1, right? You'll see this in different fonts, but this is the end result. So for example, instead of doing this, maybe they give you the limit as x approaches 0 for, let's say, x over sine of x, right? This is still going to be equal to 1. Because if the sine of x over x is going to be equal to 1, then obviously the reciprocals are still going to be equal to 1. So that's just something that they may throw you off. They may also throw you off by saying the limits as x approaches, again, this is only when x is approaching 0. As x approaches 0 for 2x over sine of 2x, for example, again, this is going to be equal to 1. As long as the x's are the same over here on both sides, it's still going to be equal to 1, right? That's just something to bear in mind. So 2x and 2x, or x and x, still going to be equal to 1. Cool. Let's go back to the original expression over here. So this is the original expression. Again, it's really important that you know how to manipulate your equations now. So if you have a look at this particular thing, you can see that, okay, so how would I look at it? How would I approach this thing? My first thing is I always ask myself, can I actually plug in the value directly, right? That's always going to be the first thing you're going to ask yourself. Can you plug in the value directly? You're going to find out that, no, unfortunately, you can't plug in the value directly, all right? So I can't plug in 0 directly because the denominator is going to be equal to 0. So I have to do some fancy math tricks, number 1. Number 2, I notice that it's the limit as x approaches 0, and I'm noticing another trigonometric ratio. So if I can somehow find it so that I can say limit as x approaches 0 for sine of x over x, if I can somehow find that somewhere in this expression, or even the reciprocal of that, then I already know that that's equal to 1, and that's going to save me a whole lot of time, right? So what do they do over here? This is a double angle identity. I spoke to you guys about the 3 different forms, right? There's the cos squared x minus sine squared x. There's the 1 minus 2 sine squared x form, and there's going to be the 2 cos squared x minus 1. But I know that there's no specific like rule or whatever that helps me with cos. It's that's as easy as like sine of x over x is equal to 1. But I do know that 1 exists for sine. So I'm not going to use this because this introduces cos, and I don't need cos right now, unfortunately. This introduces, this still has cos, and I don't want cos, but this has sine. So I want to replace this with the version of the same thing that has sine. Now that's this minus 1, right? And obviously, I can take this and I can take this, they cancel each other out. I'm left with -2 sine squared x over x squared, but you should know that the limit of a constant is just going to be that same constant. So I can take this constant and I'll pull it out of the limit expression and leave it outside over here. I'm left with sine squared x over x squared, right? Which is not what I want, really. So I have -2 limits as x approaches 0 of sine squared x over what. So I don't want that. I know sine of x over cos of x, but I can rewrite this as sine of x over x, right? I say cos of x, I mean x, sine of x over x, and the limit as x approaches 0. You should know that the limits can go even inside of a square root. So inside of a square. So even though this is square, right? The limits can go inside of that, and the limits will look like this, and I can put the square as such. So that's -2. This is really helpful now, because then I can then just say that this is -2, and I know that inside here, the limits in this thing over here is equal to 1, and then I'm squaring that. That's going to be equal to -2. So for trig type questions, most of the time, where you see the limits as x approaches 0 and you can't plug things in directly, what they're trying to make you do is to manipulate the expression somehow to find a sine of x over x, or a sine of 3x over 3x, something like that. You have to do some manipulation to get something like that. That's the essentially the end objective. Okay. Any questions on that? Cool. A second, I need to get more water. Okay. All right, so we are going to be jumping through jumping over some sections, unfortunately, because there just isn't time for that. But we're going to be going to derivatives now. So what are we jumping over type stuff? Like the type of questions, for example. Let me just share the thing real quick so that you guys can see which type of questions that you should maybe try to revise on your own, because it's going to be, we're not going to have time to really do that right now. Let me see, window. I want to go to. I can't really see it right now. Okay. Okay. The type of question that we're not covering right now. The type of question that say, let me just copy one of those types of questions so that you can make sure you study those and stuff. These types of questions. Okay, so I'm gonna paste it just now. Okay, so the type of question with piecewise functions like this, right? So piecewise function with this type of a thing. Oftentimes you'll see it asks you stuff like continuity and those types of things. Unfortunately, I don't have the time to do that right now. Like they'll ask like continuity, is the function continuous at -1 or whatever, but just make sure you're just checking the continuity principles, right? How do you do that? You check the limits as you're approaching from the left-hand side and the limits as you're approaching from the right-hand side, and you check if you actually define at that specific point, right? So in fact, that might actually be what they're making you check right now. Okay, they actually make you check for continuity over here. As you can see over here, the limit from the left-hand side is equal to 4 over a. The limit from the right-hand side is equal to 2 plus 2a. Can that be written as 4 over a? Let me see. 2. Okay, okay. I'm not going to do that right now. But okay, but probably not. Right? And then you see where you actually defined over there, right? Remember, the left-hand limit has to be equal to the right-hand limit has to be equal to what you actually define at that specific point. And if that's the case, then you're probably continuous at that specific point. We don't have the time to do that right now. We're going to go into derivatives. Again, if I cut off and you want to understand derivatives or whatever, just give me like 2 minutes, I think, to reconnect. Yes, is that a question? Okay, okay, I thought someone had a question. If not, I'm going to just proceed then. All right, so to go on, we're going to talk about derivatives, okay? It's beyond the scope of this session to speak about these, where derivatives comes from and whatever. So all you need to know is your derivative rules. Those are, you need to know them. There's no way around it. So the basic derivatives are or what's important for now, right? So we can start with just the basic derivatives, right? So there's specifically they call differentiation rules. So let me just copy them real quick, so we can just look at them real quick together. Okay, so something like, okay, and I want to throw one more in, and that is the derivative of square root of x is equal to 1 over 2 root x. Just memorize it. I know that you can technically square root of x the same as x to the power of a half, and you can figure it out from there, but it's going to save you so much time than trying to use the power rule to try to still get to the same answer, right? It's just so much easier for you to just use know that the square root of x is equal to 1 over 2 root x. So these are the differentiation rules that you should know. I'm hearing something. I'm assuming there's something happening in chat. I can't see it. You can't see it. Yeah, that's correct. My apologies. I switched it off. Okay, sorry. Thanks for pointing it out. All right. So, okay, so this is what I was trying to show you guys now. We have the different rules, this rule, this rule, this rule, this rule, this rule, this rule, and I just wanted to throw in one more, which is root x is equal to 1 over 2 root x. Those are the fundamental derivative rules, right? And again, like I was trying to say is that root x can be rewritten as x to the power of a half, right? And then you can apply the power rule, but that's going to take so much more time because you're going to put the half in front. You're going to say x is equal to 1, a half minus 1, which is the same as a half minus 2 over 2. That's going to be a half. It's going to be x. That's going to be negative a half over here. And then you're going to say 1 over 2. Obviously, the negative means that you can go to the opposite side. It's going to be x to the power of a half. And then the half just means it's the square root. So x, the square root of x, whatever. It's instead of doing these 1, 2, 3 final answer, it's best to just go straight away into the final answer, right? So that's just something to memorize that you should know. So point is, start over there. But that's not all that you're going to have. You're also going to have the derivative of tan of x. That's another thing that you should know, and that's, I think, is secant squared x. Tan of x is equal to secant squared x. So those are the basic derivatives. In fact, let me just triple check. I'm pretty sure that is the case, but I don't wanna lead you astray the night before. Derivative of tan of x is secant squared x. Yes, okay, cool. All right, so these are our basic derivatives, and you'll notice a very crucial thing over here. Okay, am I cut off? Okay, sorry. I'm just double checking that I have not disappeared. But if I do disappear again, I want to just preface this by saying if I do disappear, I will rejoin within 2 to 3 minutes. So do wait for me. And then we'll finish off with the chain rule, power rule, that's what's right. So anyway, so this is the one thing you need to memorize, and the final thing you need to memorize is going to be the chain rule, product rule, quotient rule, and the power rule, I do believe. Not the power rule, the chain rule, the product rule, and the quotient rule. I think those are the main ones. Yeah, chain rule, product rule, and quotient. I can't think of any. Well, the power. Okay, yeah, okay. Okay, so let me just copy these real quick. Because these are the other rules that you need to memorize. Okay, so these are the other sets of rules that need to be memorized, right? Particularly, obviously, you have this memorized, then you'll have this memorized along. This is just advice. I just advise you to learn this to save yourself some time instead of the power rule. And then we're going to know the product rule, the quotient rule, and the chain rule. Okay. The easier ones are the product rule and the chain rule. So I'm gonna the product rule and the quotient rule. So let me talk about that. Quotient just means divided, product just means multiplied, right? What does this basically mean? Let's say you are given a function that is x squared. And this function is being multiplied by another function, which is going to be 1 plus x, right? These are the product of two functions. I could use the power rule. How would I use the power rule? I'm going to multiply everything out. X squared plus x cubed. In this case, the power rule is probably going to be the faster method that you're going to use. So once you have written it out like this, it's still the same thing. Then I can differentiate this expression. The power rule says that I'm going to take this number to the front, 2, leave the x, and then subtract 1 from the numerator, plus. And then do the same thing. Take numbers to the front, 3, leave the x, and then minus 1 from the numerator squared, right? But when these things get particularly more complicated and well, I was going to say complicated and complex, that's the same thing. But when they get more complex, it's not going to be as easy as this. So that's where the product rule comes into play. So let's answer the exact same thing, but now with the product rule. So to answer this exact same question with the product rule, how would I go about doing this? Well, then I would say 2x. I would say 2x. I would say 2x. I would say 2x, and I would say sorry. I'm not even explaining the principles properly. All right, so let me explain the principles properly. The product rule is really simple, right? The difference in the product rule is I don't like this version of the chain of the quotient rule, because it makes me try to memorize another thing. Like, I like to keep things as simple as possible. Another way to write, that's not the quotient rule. Another way to write the quotient rule is as follows. You basically take out a negative, right? Okay, I don't know which version you guys learned. I'm just gonna say the one. But just make sure you stick to one. But I'm explaining my way. So this is one way to rewrite it. But I could also factor out a negative. So I could say negative, and I will say, and if I take out that negative, then okay. Okay. I think I'm still connected. I switched to my Wi-Fi really quickly. My hotspot rather. Okay, so I should still be connected. But okay, yeah. Okay. Anyway, the version that I prefer is, you know what? Yeah. Okay. The version. Okay. It depends which version you prefer. I prefer the version that goes like this: negative, and then I'm going to then have I'm going to have the negative outside over here. And I'm going to have f prime x gx. Then I'm going to have minus. I'm going to have f of x. Then I'm going to have g prime x over here. No, that's not what I have. Let me just fix this real quick. Over and be g x all squared. Okay, so what you'll notice is that this should actually be a plus. Okay, so it depends which version you prefer to use over here. The version that I have over here is one where I factor out the negative, and obviously you can see how the algebra works out. And then you could also have the version whereby wait. No, sorry. Even in this version, sorry, this should be a negative over here. Okay, regardless, there should be a negative over here. All right. So in this specific case, how do I basically use this expression? Okay. So this is what I prefer to use, but just for all intents and purposes, I'm going to use again. Just use the equation that you used to. I don't want to confuse you. But anyway, the quotient rule, the product rule, just memorize them. Right. What do you do over here? I think of it as follows now. When you have the product of two functions, you differentiate the first one, leave the second one unchanged, multiply them by each other, plus leave the first one unchanged, differentiate the second one. So in simple terms, I'm going to say differentiate the first term. That's going to be 2x, leave the second one unchanged, 1 plus x, plus leave the first one unchanged now, x squared, and then that's going to be, and this is going to be 1 plus x, 1 plus x, 1. Sorry, so it's gonna be 1, right? The derivative of that expression. Then you can multiply it out. You're gonna have 2x plus 2x squared plus x squared over here. It's gonna be 2x plus 3x squared. You'll find it's the exact same answer that we had calculated previously when we had used the power rule, right? So whichever rule that you use, you're still gonna arrive at the same answer, whether it's the power rule or the product rule. But oftentimes the product rule is going to be the easier method if they give you a product of two functions, right? So that's just something to bear in mind instead of using the power rule. So that is essentially that. And the quotient rule is just literally, again, the exact same principle, whereby then you differentiate the first function, you differentiate the numerator, multiply by the denominator unchanged, subtract instead of plus, and then you're going to subtract, you're going to have the numerator that's going to remain unchanged, multiply that by the denominator, which you're going to differentiate, right? And then you're going to have over denominator squared. So that's just something to bear in mind, and that is going to be particularly important. So that's the product rule, that's the quotient rule. Now we have the chain rule. Now there's a really sexy problem that was in the past, that was in the TUTS that we guys wrote, that use a chain rule, whatever. I'm saying you guys as I didn't write the TUTS myself. I wrote the TUTS obviously, but it was a chain rule problem. I'm gonna try and look for the past the TUT that we wrote. So there've been, I think it was TUT 5 or TUT 4, which was a chain rule type problem. So I want us to cover it because I think if you understand that, you're going to really be fine as far as, yeah, I think it was this one. Yeah, okay. This is really okay. This was product rule. This was product rule. So we're gonna do this product rule type question. And that is as follows. Okay, so this is very loaded, right? So bear with me. We're gonna first do a product rule type question before we do a chain rule type question. So this is just a product rule type question first, which is this one. Okay, cool. So you have a product of two separate functions, right? And we're trying to find okay, you said that h, I, and L are differentiable functions. So there's h, there's I, there's L. And then we're looking, and we know that L, and then L of x is equal to this and this. And we also find the second derivative of L, and then we need to multiply, and then we need to plug in 5 into that. So first of all, to find the second derivative, you first have to find the first derivative. So let's find the first derivative. L prime of x. This is us applying the product rule. What does the product rule say? The product rule says the following. You're going to differentiate the first function multiplied by the second function unchanged plus the first function unchanged multiplied by the second function derivative of that. Right, that's going to be, sorry, that's a little bit misleading. Let me just remove that real quick. So that is going to be the first derivative, but we can't stop there. We need to go to the second derivative. So I'm going to go another level. The second derivative. The way derivatives work is I can just work with this on its own, and then I can work with this on its own, right? So again, I'm going to find the derivative of this portion over here. What does this mean? I'm going to differentiate the first function, leave the second one unchanged, and then plus, right? This is still to find the derivative of this first one over here, and then plus, and then I'm going to differentiate the second function, right? And then leave the so then I would differentiate. So I would leave the first function unchanged, and I would differentiate the second function, right? This is going to be for the derivative of this region over here, because the product rule needs to give you two terms, right? But then we have to apply the product rule again, but now for this second portion over here. So again, I'm going to do this product rule, but now I'm going to do it for the second half of the thing, right? So for the second half is going to be as follows. It's going to be still the, it's going to be plus, and then we're going to have the derivative of the first function, h of x, multiplied by the second function unchanged, the second function unchanged, right? And then plus, then the first function we don't touch, and then we multiply by the derivative then of the second function. And in that stage, we're going to have over here. All right, and then you can simplify this, of course, and then that's going to, and then this is the second derivative. And then the last thing is just to plug in 5 everywhere, 5, 5, 5, 5, 5, and then you check which 5 you're going to be using, and then you're going to, and the rest is just algebra. So that is going to be that. Okay, so that's going to be how you use the product rule, and the quotient rule is really just the same, except now in this particular case, as you can see over here, right, you have a quotient of two functions. You have this function, you have the quotients of that function. You're trying to find j prime, whatever. You just apply the quotient rule. Again, you just need to memorize that. Now the most complicated one, the most loaded one, is going to be the chain rule. First of all, where does the chain rule come from? The chain rule comes from simply compound function, right? In the sense that the following, you have f of x. Let's say f of x is equal to sine of x, right? But then g of x is equal to 2x. So when do you use the chain rule? Anytime where you don't see x inside, right? Anytime where there could have been an x in this. Okay, let me put it this way. Anytime where there could have been an x in any of these guys, but there isn't. So where there could have been x over here, where there could be an x over here, an x over here, an x over here, anywhere where there could have been an x, but there isn't, we're going to apply the chain rule. So what does a chain rule mean? A chain rule means that okay, why is it called a chain rule? You're creating a chain of derivatives, right? What do I mean by that? This is sine of x, f of x, right? G of x is equal to 2x. I put g of x inside of sine of x, I get sine of 2x, right? And then I can then find my derivative for this particular function, sine of 2x. What is the derivative of this particular function? Well, it's not, typically, if it was just sine of x, the derivative would simply be cos x, but it isn't. So how are you going to do this one? You're going to first of all differentiate it almost normally, almost as though you were just differentiating cos of x, sine of x, right? So it's going to be cos, but just instead of saying cos of x, first of all, you can just say cos of 2x, because obviously it's 2x over here, right? And then the most important part is you're going to do multiply by the derivative of the function inside. So that's going to be multiplied by the derivative of this function. In other words, multiplied by 2, multiplied by 2, right? That's going to be the chain rule, right? That's going to be one application of the chain rule, right? Let me show you another application of the chain rule. There's another application which is as follows, right? I could say x plus 2. I could say squared. This is just an easy version. In this version, one way to do this is you could do the following. X squared plus 4x plus 4. You just multiply everything out, and then you just differentiate normally. So that's going to be 2x plus 4, and that's going to be it, right? But sometimes the question might be more complicated, but I'm just going to use a simple example to illustrate this. Again, you can imagine this could be an x squared, right? But you put x plus 2 inside of x squared. So what are you going to do? You're going to differentiate as though it's just x squared. How do you differentiate x squared? You take the 2, you bring it to the front, and it's one from the exponent. So that's going to be 2. It's going to be x plus 2, and then that's going to be to the power of 1, right? But then there was a function inside, right? So again, okay, this is not the best example, obviously, because then you're multiplying just by 1, because that's the derivative of the interior function x plus 2. Multiply by 1, that gives you 2x plus 4. Still the same answer, right? So let me do a little bit more complicated. Let me say 2x, right? 2x plus 2 squared, that's going to be 4x squared. That's going to be 8x over here, and then that's going to be plus, yeah, that's gonna be 4. So let me x, and it's gonna be plus 4. 4x squared plus 8x, plus 8x plus 4, right? And then from here, I can then differentiate this one. That's going to be equal to 8x plus 8, right? Now let me do the exact same thing now for the other guy over here. So again, the chain rule tells me first to differentiate the outside function. It's called the outside inside rule as well. You differentiate the outside function almost normally. It's going to be 2 multiplied by 2x plus 2 multiplied by the derivative of the interior function. The interior function here is 2x plus 2. So I just multiplied by 2, right? So then that's going to be 2. That's going to be 4 multiplied by 2x plus 2. That's going to be 8x plus 8. Same answer, right? Sometimes this method would have been faster, but if they have thrown in like a 3, then or just that 3 over here already makes it a whole lot more complicated, in which case it'll be easier for you to just use the chain rule in this case. Now let's talk about a chain rule that is a proper chain of functions. So I could put a function inside of a function inside of a function. I'm not going to go too crazy on you guys, but the basic principle is still going to be the same. I could say sine of cosine of root x, root 2x. Let me do that. So now I'm really like throwing a nail in, like I'm not making it easy, right? So in fact, let me ask you guys to give this to me. What's the most outside function? So give me the most outside function as though it's just a base function. So don't tell me what's inside it. Just tell me like if it was just a normal function without a cos or a sine or whatever, it's just an x. What would that most outside function look like? What's the most outside function? Can someone write it or unmute yourself and just say it out loud? Sine of x is correct. So sine of x. And now give me the function just directly inside of sine of x.
Would it be cos of x?
That is correct. Cos of x. Now give me the function directly inside of cos of x.
Root 2x.
Yes, but I don't want that just yet. I want you to just give me like the next, like just as a base. So as a base is going to be root x, right? And then there's going to be a function now inside of that. So what's that function that's inside of the root x itself as well?
2x.
2x, that is correct. Okay, so that is it, right? And then obviously 2x is really as simple as it basically gets, right? So now you can see properly how it looks like a chain. I've put a function inside of a function inside of a function. So how do I apply the chain rule in this particular case? First of all, I'm going to differentiate almost normally. But I say almost because normally would just be cosine x. But obviously instead of cosine x, I'm actually going to use the real function that's inside of here. So first I'm going to differentiate the most outside function normally. How do I differentiate? That's going to be cosine, but cosine of whatever was already inside. So the inside was already cosine of root 2x, whatever, right? And that's going to be that. But I'm not done. I'm not done for this outside function yet. I need to multiply then by the derivative of the function that's inside of that. What's inside there? Inside there, we have cosine of x. So we're going to multiply by the derivative of cosine of x, right? Specifically cosine of root 2x. So we're going to do that. So what's the derivative of cosine of root 2x? Well, that's going to, first of all, let's just differentiate cosine of x normally. That's going to be negative, right? Negative cosine of root 2x, but we're not done because there's a function inside there. So we multiply by the function that's inside of cosine of x, which is root 2x, right? But root 2x shouldn't have been root 2x. It could have just been root x. So there's even a function inside of that. So first of all, the derivative of just a regular root 2x function, like I told you, please memorize that, will just be 1 over 2 root x. But specifically in this case, is 1 over 2 root 2x, right? But we then need to multiply by the derivative of the function that was inside of that. And then can someone please give me the final thing that I'm multiplying by over here? What's that final thing? The final number in our chain. Any others? 2 would be correct. So we multiply by 2 and we are done. That's really as simple as you get. You can't say that there's a function inside of that or whatever, right? So as you can see over here, I had to go through a chain of each of the functions that we had. So hopefully they're nice to you and they don't give you something this loaded. But as you can see, there was a function inside of a function inside of a function inside of a function inside of a function. And that's basically why we have to apply a chain for each of these, right? Because you can't just differentiate normally when there's a function inside itself. Now they could like load these things up. So they could do something like sine of 3x multiplied by cosine of, let's say, 2x minus root 3x over, and then they'll say over, let's say, like x squared or something. You'll notice that you're going to have to apply the product rule over here, right? You have to apply the product rule over here. But you can't just use a product rule, because when you're doing the derivatives of that, you have to apply the chain rule over here. When you're using the chain rule, you need to remember that after you do the chain rule, you still have to apply the quotient rule for everything. So you need to be really careful in this particular case for these types of loaded questions, because then they're going to just keep on putting a question over, and they're going to put like a product rule and a quotient, a product rule and quotient rule and a chain rule all in the exact same problem. You just need to be able to identify them. So how do we identify each of these? We identify a power rule when you have an exponent as a base and a variable. Sorry, that made no sense. That makes no sense. You have a variable as a base and you have a constant as an exponent. In this case, you're going to use the power rule. You use the, I don't know if you guys actually did this thing, but you use the exponent rule when you have a constant as a base and a variable as an exponent, right? A constant is a base, so this can be the exponent rule, right? You use the product rule when you have two functions multiplying each other out, That's going to be the product rule. You use the quotient rule when you have two functions being divided by each other. So you have, oh gosh, my second. Oh gosh, okay, wait, give me a second. The pen is not working out. Okay, when you have two functions divided by each other like this, that's going to be the quotient rule. And then you're going to use the chain rule when you have a function inside of a function. So something like this is going to be equal to, you're going to use the chain rule over. Yeah, right. And formally speaking, the chain rule would look like this, right? Remember, we differentiate the outside function whilst leaving what was inside it the same. And then we're going to multiply by the derivative of the inside function. This is how you'd write the chain rule formally and stuff. So sometimes they won't give you like specific details and stuff. They'll just like give you things in terms of X and F and G or whatever. This is how you basically like help yourself and rewrite it and stuff. So for questions like, for example, this question we covered now, this question that you get given like 3, right? So make sure that you obviously know what you're doing. So in this case over here, they said h of x multiplied by I of x, but they could have given you h of like I of x and ask you the question based off of this. So know that when you differentiate this one, you differentiate the outside function whilst leaving its contents untouched, and you're going to multiply by the derivative of its contents. So the derivative of its constant, if there's a constant inside of that itself, then you're going to just keep on applying the same thing and then create a chain of derivatives, hence the name chain rule. All right, so that concludes our revision. The person who had asked, thank you, under Lawrence. Yeah, that covers, well, did that cover like the queries that you have, or do you have any other specific chain rule type questions?
No, that covers everything. Thank you.
That's yours. All right, guys, that's basically it. The recordings take a while anyway, and also I have load shedding, so I don't want to like finish my battery percentage anyway. So yeah, I'll probably upload it like midnight, 1 a.m. or something on a Google Drive, and I'll send it in the group again. I'm just gonna send the group one more time for anybody who might have missed it the first 2 times or 3 times, coming in since it. And also just as a heads up, like I want to like do like free sessions for Eng Maths and Applied Maths either on a weekly basis or like every 2 weeks. But then what I will do for like, so those are going to be free, but then I'll have like a paid version. So if you want like videos of myself going through like the past paper questions, the TAT questions, the past TATs, the current TATs when you write and stuff, I'll give more details on the group chat, but not now. This will be like after recess. So let's first enjoy recess and stuff. But for, yeah, I'll be uploading a couple of other videos because I think I need to, the foundation has to be strong because everything's going to build up on top of each other for the second half of the semester. So make sure that you catch up during recess because it's only going to get a whole lot faster and a whole lot deeper and a whole lot harder in second semester. So yeah, just a heads up. Okay, that's all for me. If you have any other further questions, please on the group chat, unless it's personal, in which case obviously feel free to DM me, but I do prefer to have everything in a single place in case people have other questions and stuff. And yeah, you'll receive the recording once lights are back. And yeah, hope you found this helpful, and I'll see you in probably another session that I'm going to hold sometime.